supernova brightness could outshine the moon for weeks. One night you step outside to lock the door, and the shadows look wrong. There's light everywhere, pale and silvery, pouring over rooftops. You glance up, expecting a full moon, but there are two. One's the usual round face you know, and right beside it, a brand new point of light blazes like a diamond on fire. It's so bright, it stings your eyes. That's what it would be like if a star near Earth exploded, a supernova so powerful it could outshine the moon for weeks. So what's actually happening when that new star appears? A supernova is what's left after a giant star runs out of fuel. For millions of years, that star balanced its own weight with the energy from nuclear fusion, atoms slamming together and pushing outward. But once it burns through its last bit of hydrogen and helium, gravity wins. The star collapses in on itself at incredible speed, and then, boom! The outer layers rebound outward, releasing more energy in a few seconds than our sun will give off in its entire lifetime. If one happened close enough, say within a few dozen light years, it wouldn't just be a twinkle in the sky. It would be bright enough to cast shadows on the ground. You could stand outside at midnight and still read a book, no flashlight needed. And it wouldn't fade quickly. For days or even months, this eerie second sun would hang in the sky, outshining everything except daylight itself. That light isn't fire, it's raw energy. The explosion sends out light across every wavelength, visible, ultraviolet, X-rays, gamma rays, all racing through space at 300,000 kilometers per second. And when it finally reaches Earth, we're witnessing an echo of the past. The star actually died long ago. Its light just took years, centuries, or even millennia to get here. Think about that. When ancient Chinese astronomers saw a guest star in 1054 that lit up their sky, they didn't know they were watching the death of a star 6,500 light years away. That same explosion left behind what we now call the Crab Nebula, still glowing faintly through telescopes. Now imagine that happening close enough for everyone alive to see it. Cities would dim their lights at night just to witness it. Social media would explode with theories, apocalypse signs, alien beacons, you name it. Some people would stay up all night just staring at it. Others would cover their windows because they couldn't sleep. And for a few surreal weeks, the world would look permanently moonlit. Then, slowly, it would fade. The second moon would shrink, turn golden, then red, and finally disappear, leaving behind only a memory and a strange realization. That dazzling light we saw came from something that died long before humans even existed. We'd be watching the universe's funeral fireworks, thousands of years late, but still bright enough to blind us with beauty. Gamma rays arrive before visible light. You wouldn't even see it coming. Before a nearby star explodes, before the sky lights up, before anyone points a telescope in awe, the first thing to reach us would be something completely invisible. A silent wave of gamma radiation, screaming through space at the speed of light. Think of gamma rays as the universe's most aggressive form of energy. They're the same stuff used to sterilize medical equipment, but multiplied trillions of times. When a massive star collapses into a supernova, it releases a flash of these rays, a brief, high-energy burst that can cut through space, atmosphere, and sometimes even lead shielding. The weird part? They arrive first. Visible light, the glow we actually see as a bright star, takes a while to escape the chaos of the explosion. Inside the collapsing star, photons bounce around for hours, days, or even months before escaping into open space. Gamma rays, on the other hand, are born in the deepest, hottest layers and shoot straight out, unfiltered. So by the time we actually see the supernova brighten the night sky, Earth has already taken the invisible hit. It's like getting smacked before you even realize someone swung at you. If the explosion were close enough, say within a few dozen light years, the impact could be devastating. Our atmosphere usually protects us from most cosmic nastiness, but a nearby gamma-ray flash could strip away parts of the ozone layer. That means sunlight's UV radiation would pour straight through, roasting crops, bleaching oceans, and frying DNA. It wouldn't vaporize people instantly, but it would quietly damage everything that depends on sunlight to live. And here's the creepy bit. You wouldn't feel the thing when it happened. No sound, no flash, no shockwave. Just a wave of invisible energy passing through you, through every living thing, while the night sky still looks calm and normal. Only hours later would the visible light arrive, announcing what had already happened, the death of a star, and maybe the beginning of a crisis on Earth. Astronomers think events like this have happened before. There's evidence that a gamma-ray burst might have hit Earth hundreds of millions of years ago, possibly wiping out a chunk of ocean life. It's one reason scientists keep such a close eye on massive, unstable stars nearby, because if one of them points its invisible beam even slightly our way, there's not much we could do about it. Gamma rays don't care about distance the way sound waves or shock waves do. They travel clean and pure, straight across the galaxy, and if they're aimed right at us, they hit without warning. So when a supernova finally lights up the sky and everyone gasps at the beauty, remember this unsettling truth. The universe already punched us hours ago. We just didn't see it coming. A supernova neutrino wave would pass through Earth in milliseconds. If a star exploded near us right now, trillions of particles would already be rushing straight through you. You just wouldn't notice. They're called neutrinos, ghost particles. They don't glow, they don't bounce off things, they don't even slow down for planets. Every second, tens of billions of them fly through your body from the sun, from deep space, even from nuclear reactions on Earth. You've been marinating in them your entire life, and they've never once touched you in any meaningful way. Now picture a supernova. When a massive star collapses, the pressure is so extreme that atoms are literally crushed into new forms. Protons and electrons fuse into neutrons, creating the dense core of a neutron star. And in that instant, the star releases an unimaginable flood of neutrinos. It's like opening every fire hydrant in the universe at once. This blast doesn't crawl through space. It races at light speed. The wave would hit Earth in just milliseconds, long before any visible light escaped the dying star. And it wouldn't matter where you are, on a beach, in a basement, deep underground, you'd be washed through by a cosmic tide of invisible energy. But here's the wild part. It wouldn't hurt. You wouldn't even feel a tickle. Neutrinos don't collide with matter very often. Maybe 1 in a trillion gets caught. They pass through solid rock, steel, and even the entire diameter of Earth, as if the planet isn't there. In those few milliseconds, that wave would slice through everything. Oceans, mountains, cities, you, and be gone before anyone even realized it arrived. The only reason we'd know it happened is because of detectors like Japan's Super Kamiokande, giant underground tanks of ultra-pure water lined with light sensors. When the occasional neutrino hits a water molecule, it produces a tiny flash, like a cosmic fingerprint. In 1987, astronomers detected a burst of just 24 neutrinos from a supernova in another galaxy. That was enough to confirm that we had just witnessed the death of a distant star. Proof that these ghostly messengers really do announce cosmic catastrophes before light ever arrives. So if a nearby supernova blew tomorrow, neutrino detectors all over Earth would light up for a fraction of a second. Computers would scream alerts. Scientists would sprint to telescopes, and only then would we wait for the light, knowing the star was already gone. It's eerie, isn't it? A silent warning that passes through every human, every creature, every atom, but leaves no mark. A cosmic whisper saying, "It's begun." By the time we look up and see the brilliant explosion in the sky, that neutrino wave will be ancient history, long gone, having passed through Earth faster than a blink. The universe doesn't always shout its warnings. Sometimes it whispers them, and those whispers can move faster than light we can see. The shock wave takes thousands of years to physically reach us. Here's something that breaks your brain a little. When a star explodes, the boom doesn't actually arrive until thousands of years after you've already seen it. That's because the universe doesn't behave like the movies. There's no sound in space, and nothing moves faster than light. So when a supernova goes off, the first thing we get is light. Bright, blinding radiation racing through space at 300,000 kilometers per second. That's instant compared to everything else. But the physical shock wave, the actual expanding cloud of star guts tearing through space, moves much slower, more like a few thousand kilometers per second. Fast by human standards, but snail-paced on a cosmic scale. Imagine the star as a massive grenade. The light is the flash, instant, blinding. The shock wave is the shrapnel. It takes time to arrive. Only in this case, that shrapnel is an expanding sphere of hot plasma, radiation, and debris spreading across space for millennia. If the star was, say, 100 light-years away, we'd see the light after 100 years, the flash in the sky, the cosmic fireworks. But the shock wave? That might take 10,000 years or more to actually reach our solar system. By then, the supernova would already be ancient history. Humanity might not even exist anymore. When it finally does arrive, though, it's not a gentle breeze. It's a wall of energized gas moving at millions of miles per hour, plowing through space dust, compressing gas clouds, and reshaping the galaxy itself. Astronomers call this expanding remnant a supernova shell, and it's basically the universe's recycling program. Those clouds of debris carry elements like iron, calcium, and gold, the building blocks of future planets, and even life itself. So, ironically, the part that takes the longest to arrive is the part that actually builds things. It's slow, but creative. That shockwave will eventually seed the cosmos with the materials needed for new stars to form, maybe even new worlds like Earth. It's strange to think about. Light announces the death, but the shockwave spreads the afterlife. And if it ever got close to us, well, it wouldn't be the apocalyptic explosion Hollywood loves to show. By the time it reached Earth, it would be a thin mist of gas, moving at incredible speed, still dangerous to satellites, possibly capable of messing with our heliosphere, but not an instant annihilation. More like a silent pressure wave from a disaster that happened long before our species learned to walk upright. In short, a nearby supernova would blind us with light long before it ever touched us. The visible explosion would fade, the world would move on, and thousands of years later, long after we're gone, the shockwave would finally arrive, a ghost from a long-dead star quietly brushing past our planet's orbit. The universe takes its time delivering consequences. Light shows you the event. The shockwave reminds you it was real. Picture the sun as a kind of cosmic campfire. Around that fire is a bubble, invisible but real, called the heliosphere. It's made of solar wind, a constant stream of charged particles blowing outward in all directions. This bubble is our force field. It shields the solar system from most of the galaxy's radiation, cosmic rays, and other space nastiness. Without it, Earth would be sitting naked in a storm of high-energy particles. Now imagine something enormous happens nearby, a Type II supernova, the explosion of a giant star 10 or 20 times heavier than our Sun. In a single instant, that dying star releases more energy than the Sun will emit over its entire lifetime. The blast doesn't just shine, it pushes. It sends out a front of radiation and charged matter so intense that it can squeeze our protective bubble like a balloon under pressure. That's what compressing the heliosphere means. The solar wind that normally pushes outward meets a far stronger force pushing inward. The boundary of our safe zone, which normally sits about 100 times farther out than Earth's orbit, could suddenly shrink to within the orbit of the outer planets, maybe even inside Jupiter's path. It would happen almost instantly, because the shock front from a nearby supernova travels at thousands of kilometers per second. For us on Earth, you wouldn't see anything right away. The sky wouldn't crack open or flash red. But deep in the magnetosphere, instruments would start to go crazy. Cosmic rays that were once deflected would pour in through the newly exposed edges of space, reaching our atmosphere in greater numbers. Satellites would glitch. High-altitude flights could see radiation levels spike. And over time, the entire planet would be bathed in more cosmic radiation than our species has ever experienced. It wouldn't necessarily wipe us out, but it would make Earth's surface a harsher neighborhood. Electronics would age faster. Astronauts would be grounded. The ozone layer could erode, letting in more ultraviolet light. And depending on how close the explosion was, some regions of the atmosphere might glow faintly at night from all the ionization, like a permanent ghostly aurora. Scientists think this has happened before. Traces of certain isotopes, like iron-60, found in ocean crust, hint that a nearby supernova may have brushed against our heliosphere a few million years ago. Earth survived, but the event might have altered climate and possibly nudged a few species toward extinction. So while the idea of a space shield shrinking sounds like pure science fiction, it's a very real, very slow-motion danger. The sun usually stands as our bodyguard against the galaxy. But if a massive star dies close enough, even the sun has to take a step back. And somewhere out there, in the quiet dark, that next dying star might already be inhaling for its final, universe-shaking breath. Its blast could strip away part of our upper atmosphere. Earth's atmosphere is like an invisible blanket, thin, fragile, and holding everything we care about inside it. But that blanket isn't invincible. Under the right kind of cosmic hit, it can be torn apart. If a nearby star exploded, say a Type II supernova just a few dozen light-years away, the wave of radiation it unleashed would slam into Earth's upper atmosphere with unimaginable force. It wouldn't burn the surface directly like a laser. Instead, it would peel away the layers of air that protect us from space itself. Here's how it works. Our upper atmosphere, the ionosphere and exosphere, is filled with atoms that are already tenuously held by gravity. A supernova's radiation, especially the high-energy gamma rays and X-rays, could knock electrons right out of those atoms. That process, called ionization, doesn't just excite the air, it breaks it down. Those atoms, now electrically charged, can get swept away by solar wind or the incoming shock wave. It's like the air itself becomes loose dust and space just blows it away. You wouldn't notice it at first. The sky would look normal, clouds would still drift, wind would still blow. But above the clouds, high above the ozone layer and weather layers, our planet's edge would start to thin. The atmosphere would shrink the way frost melts from the top down. That's not just poetic, it's measurable. Scientists studying the effects of extreme solar flares already know how sensitive our upper layers are. A strong enough solar storm can erode the atmosphere slightly, but a supernova's radiation would be millions of times stronger. Losing part of the upper atmosphere has a domino effect. First, the ozone layer takes a beating. That's the thin shield that filters out ultraviolet light from the sun. Without it, UV radiation would spike at the surface, scorching crops, sterilizing plankton, and mutating DNA in every living thing exposed. Then there's the temperature drop. Less air means less insulation. Nights would become colder, weather patterns might shift. Satellites in low orbit would drag less, changing how long they stay up there. And long after the blast fades, cosmic rays would continue to pour in more easily, since Earth's natural defenses would be weakened. Here's the eerie part. This isn't a theoretical doomsday fantasy. There's physical evidence that similar events might have happened before. Isotopes like nitrate and beryllium-10, trapped in ancient ice cores, suggest that at some point in Earth's past, something bathed the planet in radiation strong enough to change its atmospheric chemistry. The fingerprints match what we'd expect from a nearby supernova. So if a star blew up close enough, we wouldn't see our atmosphere vanish in an instant. It would fade, molecule by molecule, in eerie silence. From space, Earth might still look blue, just a slightly paler shade. A planet still alive, but breathing thinner air than before. The universe doesn't need fire to destroy a world. Sometimes it just needs to take the air away. The sun's magnetic field might warp from passing shock pressure. The sun might look calm from Earth, a glowing, perfect sphere. But underneath that golden face, it's chaos, magnetic chaos. Our sun's entire surface boils with tangled magnetic loops, twisting and snapping like live wires. Those magnetic fields are what create sunspots, solar flares, and the occasional tantrum that sends plasma blasting toward Earth. Now imagine something big enough to bend the sun itself. A nearby supernova, even one dozens of light years away, could send a shock wave of charged particles and magnetic energy racing through our corner of space. When that wave finally hits our solar system, it doesn't just breeze past, it pushes. And the first thing it meets is the magnetic shield around our sun, the heliospheric magnetic field, a bubble of magnetism that stretches far beyond Pluto. That magnetic field isn't rigid, it's more like a giant soap bubble made of invisible magnetic lines. Normally, it's shaped and inflated by the sun's own solar wind. But if a powerful enough shock wave sweeps through, it can distort that bubble, press it inward, twist it, even make it wobble like jelly in a bowl. For the sun, that means temporary magnetic mayhem. The outer layers could ripple. Solar winds might spike or stall. The normal rhythm of solar storms could get scrambled for centuries. It's like hitting a giant tuning fork. The magnetic field would vibrate, and the echoes could take ages to fade. From Earth's perspective, we might notice strange things happening with space weather. Radiation levels could change. Auroras might appear in places they never have before, maybe glowing at the equator for weeks. Communication systems could glitch more often. Even the delicate balance of cosmic rays reaching our planet would shift. It's also possible that the magnetic field could briefly tilt, not permanently, but enough to throw off the pattern of solar wind flowing through the solar system. That, in turn, would affect Earth's own magnetic field, which is linked to it like a smaller bubble inside a larger one. All of this sounds theoretical, and it mostly is, but we've seen smaller examples. When intense interstellar shocks pass near our solar system, the boundary of the heliosphere, called the termination shock, can shift by billions of kilometers. The Voyager spacecraft actually measured it. The invisible frontier of the sun's influence expanding and contracting like it's breathing. A nearby supernova would be the cosmic equivalent of a punch instead of a breath. The sun wouldn't explode, but its invisible armor would bend. For a few chaotic centuries, our star might pulse irregularly, sending unpredictable bursts of energy into space. Not because it's angry, but because something bigger, older, and already dead shoved it out of shape. The universe has a funny sense of scale. One dying star can reach across light years and make another star, our star, flinch. Earth's orbit wouldn't change. When people imagine a nearby star exploding, they often picture Earth being blown out of orbit, sent flying through space like a baseball smacked by a cosmic bat. That makes for great movie drama, but in reality, the universe doesn't work that way. If a star went supernova near us, our planet wouldn't get shoved anywhere. The explosion might be unimaginably powerful, but it's still happening across trillions of kilometers of empty space. Gravity doesn't just switch off. Even after a supernova, the total mass of that system doesn't vanish. It's still there, just rearranged. So Earth's orbit wouldn't budge. The sun's pull keeps us locked exactly where we are. But here's the unsettling twist. We wouldn't need to move an inch for it to kill us, because the real danger isn't from flying debris, it's from invisible radiation. When a star explodes, it unleashes a tsunami of gamma rays, X-rays, and cosmic particles. These don't drift through space like ash. They race through the vacuum at light speed. So while the actual chunks of matter, the gas, dust, and iron fragments, would take thousands of years to reach our solar system, the radiation blast would hit us almost instantly. That radiation is what would make life on Earth unbearable. The first wave of gamma rays would slice through our upper atmosphere, breaking apart molecules of nitrogen and oxygen. Those broken molecules would recombine into nitric oxides, which destroy ozone. Within days, the protective shield that blocks harmful UV light would crumble. Then the cosmic rays, high-energy atomic nuclei, would arrive. They'd rain down continuously, bombarding everything from satellites to skin cells. On the surface, radiation levels would soar. Crops would fail. Marine plankton, the foundation of the ocean food chain, would start dying off. And the cruel irony? The debris, the tangible, dramatic part of the explosion, would be the least of our worries. By the time any physical fragments of that dead star drifted through interstellar space and reached Earth, the planet's biosphere might already be sterile. The explosion's light would fade, but the damage would linger in the form of chemical scars across our atmosphere and layers of radioactive dust settling from above. We wouldn't see flaming rocks streaking across the sky or walls of fire devouring cities. Instead, we'd watch the sunlight turn harsher and the skies shift color as radiation quietly poisoned the air. It's strange. The apocalypse would come at the speed of light, not the speed of shock waves. You wouldn't feel wind or heat. You'd just live under a deadlier kind of sunshine. Earth would still spin around the sun like nothing happened, perfectly on schedule, perfectly balanced, just orbiting through a more hostile universe. Our position in space wouldn't change at all. Only everything living on it would. The moon's surface could glassify from radiation exposure. The moon has always looked peaceful, a quiet gray companion hanging in the night sky. But if a nearby star exploded, that calm face would become something far stranger. You've probably seen glass form when lightning strikes sand. It melts the grains together in an instant, leaving smooth, glassy tunnels called fulgurites. Now imagine that happening not from a single bolt of lightning, but from a flood of cosmic radiation washing across an entire world. That's what a nearby supernova could do to the moon. When a massive star goes supernova, it emits an enormous burst of gamma rays and high-energy particles, radiation so intense it can strip electrons from atoms and heat materials instantly. Here on Earth, our thick atmosphere absorbs most of it. But the Moon? It has no atmosphere, no magnetic shield, and no protection of any kind. It's completely exposed to the raw universe. If that radiation hit, the Moon's upper surface, the dusty layer called regolith, would absorb it directly. The heat would heat the top few millimeters of dust and rock until they literally melted. As the heat dissipated, the molten material would cool into a thin glass crust, sealing over the gray powder beneath it like frosting turning to ice. That's what scientists mean when they say the Moon's surface could glassify. It wouldn't look like a smooth mirror, more like a landscape dusted in shimmering glaze, with the brightest regions near the side that faced the supernova. Future astronauts might walk across it and hear the crunch of glass under their boots. Telescopes from Earth might even catch the change, sunlight glinting differently off the new fused surface. In fact, there's already evidence that this may have happened before. Samples brought back by Apollo astronauts contain microscopic glass beads formed by ancient radiation and micrometeorite impacts. Some researchers think supernovae could have contributed to those tiny glass layers, leaving chemical fingerprints like exotic isotopes of iron or nickel buried in the dust. If another one went off nearby, we'd see it happen again, only this time in real time. The Moon might briefly shine a little brighter, reflecting light off its new glass skin. To the naked eye, it would look hauntingly beautiful, a cosmic mirror born from destruction. But beauty aside, it would also be a warning. That same radiation, powerful enough to melt rock on the Moon's surface, would be lethal to life on Earth if our atmosphere didn't block it. The Moon would become a glowing reminder of what our planet narrowly survived, a silent, scorched witness orbiting a wounded world. The next time you look up at that pale gray face, remember, it's not just rock and dust. It's history, frozen in radiation scars, a record of every violent thing the universe has ever thrown our way. And someday, if a nearby star dies again, the Moon might get another glassy layer, a new scar in its endless cosmic story. Our night sky would permanently change. Imagine walking outside one night and realizing that the constellations don't look right anymore. Orion's belt has a fourth jewel. Cassiopeia's W now has a glowing heartbeat at its center. Every night for the rest of your life, that strange new light hangs there, too bright to ignore, too steady to be a planet. That's what a nearby supernova would do to our night sky. When a star explodes, it doesn't just disappear. It leaves behind a remnant, a glowing cloud of gas and dust that can shine for thousands of years. The explosion lights up the debris, heating it and sending shock waves rippling through interstellar space. What we see from Earth is a brilliant new star that slowly fades, then a glowing ghost that never completely dies out. The ancient Chinese called these events guest stars. One appeared in the year 1054, so bright it was visible in daylight for nearly a month. They recorded it carefully, not knowing that the light came from a massive star's death 6,500 light years away. Today, that same explosion is what we now call the Crab Nebula, a vast, colorful cloud still glowing from the energy released nearly 1,000 years ago. If a supernova happened close enough today, it would carve a permanent mark into our sky. At first, we'd see it as a new, blinding point of light, brighter than Venus, maybe bright enough to read by at night. Then, as the months passed, it would fade into a fuzzy spot, not gone, but transformed. Over years and centuries, that spot would stretch and swirl as the debris expanded, forming an intricate glowing web of colors visible through telescopes. Astronomers call these scars supernova remnants, but that's too sterile a term for what they really are. They're cosmic tombstones, the ashes of stars that lived and died long before us. Every one of them tells a story of creation hidden inside destruction. If humanity lasts long enough, we'd watch that new star evolve. Future generations might see it dim, then watch its nebula spread wider, painting new shapes in the constellations their ancestors memorized. Old star charts would become outdated. The sky we've known for all of recorded history, the same one that guided sailors, inspired poets, and shaped calendars, would never look the same again. And it wouldn't just be a visual change. That light would remind us that everything up there is alive and dying, just on scales too vast for us to normally notice. The stars aren't permanent. They just live slow enough to fool us. Centuries from now, the new star would fade into a faint, ghostly ring, still glowing faintly against the dark, like a bruise in the sky. Astronomers would point telescopes at it and remember that our ancestors once saw it blaze like a second sun. A supernova doesn't just destroy a star, it rewrites the sky. And the universe, like any artist, never erases its mistakes. It leaves them there, glowing forever. Gamma rays would split nitrogen molecules, forming nitric oxide. It sounds like something out of chemistry class, gamma rays splitting nitrogen molecules. But in a nearby supernova, that's not a lab experiment. It's the moment our atmosphere starts to tear itself apart. Here's the thing. The air you're breathing right now is mostly nitrogen, about 78%. It's stable, quiet, and harmless. Those nitrogen molecules stick together with one of the strongest chemical bonds known in nature. That's why it takes lightning or specialized industrial machines to break them apart on Earth. But if a nearby star exploded, we wouldn't need lightning. Gamma rays would do the job instantly. Gamma rays are the universe's purest violence, packets of energy so intense they can knock electrons out of atoms. When a supernova erupts, it blasts a wave of these rays across space at light speed. If that wave slammed into Earth, those rays would hit the upper atmosphere first, colliding with nitrogen and oxygen molecules that have peacefully floated there for billions of years. In the chaos that follows, the nitrogen bonds snap like dry twigs. The freed atoms don't just float away, they immediately start forming new compounds, the most important of which is nitric oxide. Now, nitric oxide itself isn't the bad guy. Down here, at ground level, it's used by your own body to help blood flow and relax muscles. But up above Earth, it's a different story. Up there, nitric oxide becomes a destroyer of the ozone layer. It reacts with ozone and breaks it down into ordinary oxygen, stripping away the very thing that protects us from the sun's ultraviolet radiation. So while the supernova's light might look beautiful from the ground, that eerie moon-bright glow in the night sky, the real disaster would be invisible. The upper atmosphere would start chemically unraveling, molecule by molecule, until vast sections of ozone were gone. Without that shield, UV rays from our own sun would pour through like acid light. Crops would wither, ocean plankton would die off, and animal life would develop radiation burns even on cloudy days. The chain reaction could last for years. Nitric oxide doesn't just vanish. It lingers, cycling through reactions that keep damaging ozone long after the supernova's flash has faded. Scientists believe something like this may have happened before. Roughly 440 million years ago, during the Ordovician extinction, nearly 85% of marine species vanished. Some researchers think a nearby gamma-ray burst might have been to blame, the same nitric oxide chemistry playing out on a prehistoric Earth. So when we talk about gamma rays splitting nitrogen molecules, we're really describing a kind of invisible war. The radiation doesn't burn the planet directly, it weaponizes the air itself. And if that ever happened again, you wouldn't see the damage. You'd just notice the sunburns coming faster, the crops dying quicker, and the sky above looking perfectly normal, while quietly killing everything beneath it. Nitric oxide destroys ozone, letting UV radiation flood the surface. You can't see it, you can't smell it, and you wouldn't even know it was gone until the sunlight started to burn. High above us, about 30 kilometers up, floats one of Earth's most important layers, the ozone layer. It's thin, so thin that if you compressed it into a solid sheet, it'd be barely a few millimeters thick. Yet that fragile film shields every living thing from the sun's ultraviolet radiation, the same kind of energy that sterilizes hospital rooms and gives you sunburns. Now picture what happens after a nearby star explodes. A flood of gamma rays slams into our atmosphere, splitting nitrogen molecules apart and creating nitric oxide. At first, that sounds harmless. We use nitric oxide in medicine. Our bodies even make a little of it naturally. But up in the stratosphere, it becomes the atmosphere's worst vandal. Nitric oxide reacts with ozone in a simple but devastating loop. One molecule of nitric oxide meets one molecule of ozone, O3, and poof, out comes nitrogen dioxide, NO2, and plain oxygen, O2. The catch? That nitrogen dioxide doesn't stop there. Sunlight splits it back into nitric oxide again, ready to attack more ozone. One tiny molecule can destroy thousands of ozone molecules before finally breaking down. In other words, the air starts quietly eating itself. As the ozone thins, more ultraviolet light from the sun pours through. The difference wouldn't look dramatic to the eye. No sudden color change, no glowing sky, but the effect would be brutal. Within months, UV radiation at the surface could double or triple. Plants would be the first to suffer. The delicate tissues in leaves and algae absorb too much UV, damaging the machinery of photosynthesis. That means less oxygen produced and less food for the entire food chain. In the oceans, plankton, the base of marine life, would die off in massive numbers. And on land, animals and humans would start showing the same signs as lab rats exposed to radiation: cataracts, skin cancers, immune system failure. Even weather patterns might shift. The ozone layer also helps trap warmth in the upper atmosphere. Strip it away, and the planet's circulation changes, pushing storms and jet streams into new, unpredictable paths. And the cruel part? It wouldn't stop when the supernova's light faded. Nitric oxide lingers for years. Long after the bright new star dimmed from the sky, its chemical fingerprints would still be twisting through the stratosphere, nibbling at what remained of our planet's shield. Scientists have modeled this scenario, and it's not science fiction, it's chemistry. A single burst of radiation strong enough to make a visible supernova could drop global ozone by half. The sun wouldn't get hotter, we'd just lose our sunscreen. So if a nearby star ever does go off, the first warning won't be flames or shock waves, it'll be the sunlight itself, suddenly sharper, crueler, and far more dangerous than before. The world would still look bright and blue, but every ray of that beauty would be slowly burning us alive. Ozone depletion could last for centuries. If a nearby star ever exploded, the damage to Earth wouldn't fade with the light. It would linger, not for years, not for decades, but for centuries. We usually think of the ozone layer as something fragile but recoverable. After all, humanity poked a hole in it with CFCs back in the 20th century, and it's been slowly healing since we banned those chemicals. But that kind of damage is a scratch compared to what a supernova's radiation could do. When gamma rays from an exploding star slam into our atmosphere, they split nitrogen molecules and create nitric oxide, which in turn breaks down ozone. The result isn't a local hole, it's a global collapse. Imagine not one ozone hole over Antarctica, but the entire planet wrapped in a thinned, threadbare layer of atmosphere. And here's the real kicker. Even after the initial blast is over, the chemistry keeps going. Once nitric oxide and nitrogen dioxide are created, they don't just vanish when the light fades. They stick around, cycling through reactions that keep destroying ozone. Think of it like a chain reaction that can't stop once it starts. Every time sunlight hits those molecules, they trigger more destruction. Over time, gravity slowly pulls these compounds down into the lower atmosphere, where they wash out as acid rain. But that process is painfully slow. Models suggest that even a moderate nearby supernova could leave Earth's ozone depleted for hundreds of years before it begins to rebuild naturally. That means generations would live and die under a sky that no longer filters sunlight the way it used to. Crops would have to be genetically engineered for high UV tolerance. People might only go outdoors under protective glass domes or at night. Skin cancer and cataracts would be everyday conditions, not rare ones. Even the color of the world would shift slightly. The sky might look paler because ozone absorbs certain wavelengths of light. Sunsets could appear harsher, more violet than red. The sunlight itself would feel different, sharper, almost metallic, like standing under an overexposed photograph. And let's say humanity somehow adapts. The ecosystems might not. Ocean plankton, already sensitive to UV, could take centuries to recover. Forests at high altitudes might collapse completely. The global carbon cycle would slow, climate patterns would drift, and recovery wouldn't be a single snap-back moment. It would be a long, uneven climb through environmental trauma. There's even evidence Earth has gone through this before. Ancient isotope records, like spikes of beryllium-10 and iron-60 in ocean crust, suggest that around 2 million years ago, something bathed our planet in radiation strong enough to disturb its atmosphere for millennia. Some scientists think a nearby supernova was the cause. So when astronomers say ozone depletion from a supernova could last centuries, they don't mean the air will smell funny for a while. They mean the planet's entire biosphere would enter a slow-motion survival mode, one that might not fully heal until long after the bright guest star in the sky has faded from human memory. A single flash from across the galaxy, and Earth could spend the next 1,000 years recovering from the light. DNA mutations in plants and animals would spike. Every living thing on Earth carries a tiny instruction book inside it, DNA. It's the language life uses to build eyes, leaves, wings, and skin. But that language isn't written in ink, it's written in chemistry. And chemistry can be damaged. Under normal sunlight, Earth's ozone layer filters out most of the radiation that can scramble those letters. But after a nearby star explodes, that shield gets shredded. Suddenly, ultraviolet light, X-rays, and cosmic rays are everywhere, a non-stop storm of energy hammering every cell on the planet. And when that happens, mutations explode, literally and biologically. Radiation hits DNA like hail on a windshield. It snaps molecular bonds, knocks base pairs out of place, and sometimes even severs entire strands. Cells try to repair the damage, but they're sloppy mechanics. They glue the wrong pieces together, or fill in the blanks with random code. Those mistakes become mutations, permanent typos in life's book. At first, it wouldn't look dramatic. Trees wouldn't suddenly sprout eyes, and people wouldn't grow extra limbs. Most mutations are silent, tiny errors that don't change much. But when an entire planet's worth of organisms is suddenly exposed to 10 or 100 times more radiation than usual, the math gets scary. For plants, that means twisted leaves, stunted growth, or seeds that never germinate. Radiation can destroy chlorophyll, so forests might turn patchy and pale. Crops would fail more often, and the few survivors could carry strange genetic quirks passed down to their offspring. For animals, it gets even more personal. Reproductive cells, eggs and sperm, are especially sensitive. That means defects in embryos, birth abnormalities, or sudden changes in traits. Insects might mutate faster because of their short lifespans. Birds could start showing odd feather patterns or eye deformities. In humans, cancers would skyrocket. Skin cells and bone marrow, which constantly divide, are perfect targets for radiation. But mutation isn't all tragedy. Evolution is built on mutation. Every new trait life has ever developed, from feathers to color vision, started as a genetic error that turned out to be useful. So while most creatures would die or suffer, a few might adapt. Over thousands of generations, species could evolve resistance to radiation, thicker skins, faster DNA repair systems. In a dark twist, a supernova could speed up evolution, turning the planet into a biological lottery. Still, that lottery would come at a terrible cost. Ecosystems would collapse long before new species could fill their place. Food chains would fragment, and life would look more like it did after the great extinctions of the past, stripped down, experimental, and desperate. Scientists call it genetic pressure, when nature suddenly tests every possible combination of life to see which ones can survive. A nearby supernova would do exactly that. It would make the entire planet a petri dish, flooded in light too powerful to see, rewriting the DNA of everything that dares to live under the sun. Cosmic ray showers could double background radiation globally. Every second of every day, you're being hit by radiation, not from your phone or microwave, but from space itself. They're called cosmic rays, tiny, high-energy bullets fired across the universe. Normally, Earth's magnetic field and atmosphere catch most of them, breaking them into harmless fragments before they ever reach the ground. What's left is a whisper of radiation, just enough that your Geiger counter clicks now and then, but far too weak to hurt you. Now imagine the dials suddenly turning up, not a little, double the background radiation everywhere on Earth. That's what would happen if a nearby star exploded. A supernova is the universe's ultimate particle accelerator. When it dies, it flings out atomic shrapnel, mostly protons and heavier nuclei, at nearly the speed of light. These are cosmic rays, and they travel for hundreds or even thousands of years, bouncing between magnetic fields and shock waves until they finally reach us. If the explosion happened close enough, those high-energy particles would pour into our solar system like rain through a broken roof. The sun's magnetic bubble, the heliosphere, usually deflects most of them, but after a supernova, it could be overwhelmed. For centuries afterward, Earth would sit under a heavier, invisible drizzle of radiation. What does double the background really mean? It's not instant vaporization. It's slow exposure. Radiation from cosmic rays doesn't burn skin or melt metal. It seeps quietly into everything. It adds up. Over time, it causes DNA damage, mutations, and cellular breakdown. Cancer rates would rise. Life expectancy might fall by a few years, not because of catastrophe, but because the entire biosphere is living under a constant extra dose of radiation. Even plants would feel it. Cosmic rays penetrate deep into soil, altering the chemistry of roots and microbes. Seeds could mutate faster, leading to strange growth patterns. In animals, especially those with long lifespans, radiation damage builds up across generations. Birds flying at high altitudes would absorb more than creatures on the ground. Pilots, astronauts, and mountain dwellers would get the worst of it. There's also a secondary effect: atmospheric ionization. Cosmic rays create charged particles high in the air, which can influence lightning patterns and cloud formation. Some scientists even think cosmic rays might slightly affect weather by seeding clouds or triggering electrical discharges. So after a supernova, Earth might not only be more radioactive, it might be stormier too. And this isn't just theory. Evidence from ocean sediments shows spikes of rare isotopes like iron-60, which form when cosmic rays bombard atoms in Earth's atmosphere. Those spikes line up with times when nearby stars are believed to have exploded, roughly 2 to 3 million years ago. Earth survived, but traces of that radiation are still detectable today. So when astronomers say a nearby supernova could double background radiation, it doesn't mean the world ends overnight. It means the entire planet steps into a harsher version of reality, one where the air, soil, and even our bodies quietly hum with the memory of a star that died light years away. The universe doesn't always destroy quickly. Sometimes it just turns up the volume and lets everything feel it forever. Nighttime air glow might turn eerie green from ionized oxygen. One night, you walk outside expecting darkness, but the sky isn't black anymore. It's glowing, not from the moon, not from city lights, but from the air itself. A dim, haunting green stretching from horizon to horizon. That's not science fiction. It's what could happen if a nearby star exploded. When a supernova floods Earth with high-energy radiation, our atmosphere doesn't just absorb it, it reacts. Those gamma rays and charged particles slam into oxygen molecules high above the ground, knocking electrons loose and turning them into ionized oxygen. And when those excited atoms calm down, when their electrons fall back into place, they release energy as light, specifically green light. It's the same color you see in auroras, that luminous emerald glow that dances near the poles during solar storms. But this wouldn't be limited to the Arctic or Antarctic. It could stretch around the entire planet. Every night, everywhere, the sky would shimmer faintly green. Even on moonless nights, you could walk without a flashlight. This phenomenon already exists on a smaller scale, called nighttime air glow. Normally, it's invisible to human eyes, just a faint background light produced by molecules in the upper atmosphere recombining after being split by sunlight. But a nearby supernova would turn that gentle whisper into a shout. Those radiation would supercharge those atoms and produce a worldwide eerie glow, like living under a permanent ghostly twilight. Imagine standing in the countryside, no city lights, just that strange green haze above you. Trees would cast shadows at midnight. Oceans would reflect a jade shimmer. The stars would still be there, dimmer now, fighting against the planet's own light. The world would never truly get dark. It would be hauntingly beautiful and quietly terrifying. That glow would be a symptom, not a gift. It would mean our atmosphere is being bombarded by radiation strong enough to ionize oxygen globally. Satellites would see the upper layers of the atmosphere swelling and heating up. Communication signals would bend and scatter. GPS systems would fail more often. And the color might change over time. As nitrogen, oxygen, and other gases recombine in different ways, patches of red or purple could appear, like the whole planet wrapped in a living aurora. It could last weeks, months, or even years, slowly fading as radiation levels dropped and the atmosphere calmed down. If you could see it from space, Earth would look like a glowing marble, a green-blue lantern adrift in the dark. For early humans, something like this might have inspired myths of glowing skies or gods descending. For us, it would be a scientific confirmation. A nearby star has died, and its death has reached us. So when the night turns green, it wouldn't be an aurora. It would be the planet itself, lit from above by the memory of an explosion light years away. The sky's quiet way of saying, something out there just ended. Satellites' microchips would fry instantly. If a nearby star ever exploded, you wouldn't notice it first on the ground. The first casualties would be orbiting above you. Thousands of satellites silently dying in the dark. Our modern world lives in space, more than we realize. Every GPS ping, weather forecast, phone call, airline route, and credit card swipe relies on tiny machines floating above Earth. Each one carries delicate electronics, processors smaller than your fingernail, built to handle temperature swings, micrometeorites, and solar storms. But a supernova's radiation would be something entirely different. Gamma rays and cosmic particles from a nearby explosion would hit our planet like an invisible flood. These high-energy waves don't just bounce off metal, they pass through it. When they hit the microchips inside satellites, they unleash electrical chaos. Microchips are built with microscopic transistors, billions of them, that control current in perfect patterns. They're incredibly precise and incredibly fragile. A single gamma photon or charged particle can knock electrons loose inside those circuits, flipping a 0 to a 1, or short-circuiting an entire system. It's called a single event upset, and it's the space engineer's nightmare. Now, multiply that by every satellite in orbit, all being hit simultaneously by a storm of radiation thousands of times stronger than any solar flare we've ever recorded. Within seconds, communications would stutter. GPS coordinates would vanish, and entire constellations of satellites would go dark. Many would never recover. Even the best shielding can't stop it. The radiation from a supernova carries enough energy to rip through millimeters of aluminum or composite casing as if it were tissue paper. It doesn't melt the hardware, it scrambles it, erasing memory, frying logic gates, and corrupting power systems. Some satellites might reboot endlessly, trapped in a digital coma. Others would simply drift away, unresponsive, the sky filling with ghosts of dead machines. The International Space Station might fare better for a while, protected by thicker walls and backup systems. But even then, astronauts would have to retreat into the most shielded compartments. The radiation could blind sensors, cook batteries, and destroy delicate instruments. Back on Earth, the effects would ripple instantly. GPS-guided systems, planes, ships, agriculture machines, even emergency services would lose navigation. Internet traffic through satellite links would collapse. Weather prediction would become blind guesswork. The global economy, now dependent on constant satellite timing and communication, would lurch like a ship losing its compass. We'd still have our ground infrastructure, but it would suddenly feel like the 1950s again. Maps, radio, and uncertainty. And all because somewhere out there, a star had died and decided to send its farewell letter in gamma rays. Astronomers say radiation this strong wouldn't just flip a few bits. It would sterilize low Earth orbit. The machines we've spent decades launching would be reduced to silent debris in seconds. If that happened tonight, you wouldn't see it. You'd just notice your phone showing no signal, your GPS spinning in circles, and the sky above full of metal corpses. Proof that the universe doesn't care how clever we are with our technology. It built stars. We built satellites. And when the stars explode, ours don't stand a chance. The upper atmosphere could briefly shine from excited particles. Picture this. The star explodes. Gamma rays and charged particles race through space at the speed of light, reaching Earth before anyone even understands what happened. And then, for a few haunting moments, our atmosphere begins to glow. Not from sunlight, not from lightning, from the air itself. When that flood of high-energy radiation slams into the upper layers of our atmosphere, the ionosphere and thermosphere, it hits atoms of oxygen, nitrogen, and hydrogen like a hammer striking a bell. Those atoms absorb the energy, and their electrons jump to higher energy states. Then, as they settle back down, they release light. In other words, the sky literally shines because the air molecules are excited. To your eyes, it might look like an enormous, slow aurora, a shimmering halo wrapping the entire planet. Greens, blues, and reds could ripple across the heavens, but not like the northern lights. Those dance and twist. This would be steady, global, and eerily uniform, the whole edge of the atmosphere glowing at once, like a faint neon shell around the Earth. For astronauts in orbit, it would be breathtaking and terrifying. They'd see the horizon glowing brighter than the sun's reflection, a vast ring of light circling the world. On the ground, you might look up at night and notice a soft glow everywhere, like the entire sky has become backlit. City lights would look dimmer, swallowed by this strange atmospheric luminescence. This glow could last minutes, hours, maybe days, depending on how much energy the atmosphere absorbs. It would fade slowly as the particles lose their excitement, their electrons calming down and releasing the last of their energy into the void. But for that brief time, Earth itself would look alive with light, like it's blushing under the touch of a dying star. There's actually a smaller version of this that happens every day. Air glow. The upper atmosphere naturally emits faint light as atoms recombine after being separated by sunlight. Usually, it's invisible to us, seen only by special cameras from orbit. But a supernova would amplify that effect beyond anything we've ever witnessed. Millions of times brighter, driven by radiation so intense it changes the color and brightness of our entire sky. It would be stunning, but it wouldn't be good news. That glow would be a sign that our planet is being irradiated, that atoms high above are being smashed and charged faster than they can cool down. Satellites would fail, radio signals would bend or vanish, and the very air we breathe would start changing chemistry. Still, for those few glowing hours, It would be unforgettable. Earth turned into a lantern, lit not from within, but from the scars of cosmic energy passing through it. People would stare at the glowing heavens and call it beautiful, never realizing that it was the atmosphere's way of screaming in color, a silent, shining symptom of being struck by the death of a star. Acid rain, composed of nitric acid, would follow. Long after the blinding flash of a nearby supernova fades from the sky, the real damage begins to fall, drop by drop. Not fire from heaven, not debris from space, but it rained. And not the kind that smells clean after a storm. This would be acid rain, formed from the chemical chaos a supernova leaves behind. Here's how it happens. When a dying star explodes, it sends a flood of gamma rays and cosmic particles hurtling through space. When that radiation slams into Earth's atmosphere, it tears apart stable molecules, especially nitrogen and oxygen. Those two gases normally make up almost all the air we breathe, but under intense radiation, their bonds break, and the freed atoms recombine in dangerous ways. One of the most important of those new compounds is nitric oxide, NO. It reacts with oxygen to form nitrogen dioxide, NO2. A brownish gas that's already toxic on its own. Then, when it mixes with water vapor in the clouds, the reaction produces nitric acid, HNO3. And once you have nitric acid in the sky, you get acid rain. At first, it would look completely normal. No red color, no sizzling droplets. You'd only notice when it touched metal or plants. Over time, the rain would corrode rooftops, eat away at monuments, and leach minerals from soil. Lakes and rivers would slowly turn acidic, killing fish, amphibians, and plankton. Forests, especially those near the poles where rainwater tends to accumulate, would begin to die back. And the thing about nitric acid is it's persistent. Once it forms in the upper atmosphere, it doesn't disappear quickly. It can take years to rain out completely. Each new storm would rinse a little more of it from the sky, spreading the damage quietly, globally. We've seen small versions of this already, after volcanic eruptions or nuclear tests, when sulfur and nitrogen oxides create brief periods of acid rain. But a nearby supernova would amplify that effect 1,000 times over. Instead of local pollution, the entire planet's sky would turn into a weak acid bath. Scientists think this kind of chemical fallout could explain odd patterns in the fossil record, sudden drops in plant diversity, or sediment layers showing spikes in nitrogen compounds. They're clues that at least once or twice in Earth's past, something enormous filled our atmosphere with radiation and left it raining acid for decades afterward. For humans, it wouldn't melt your skin like in horror movies, but it would corrode our infrastructure, ruin crops, and make water unsafe to drink without treatment. It would also add to ozone destruction, since nitric acid is part of the same chemistry that eats away at that layer. So after the night sky dims and the world seems to return to normal, you'd hear the rain again, soft, steady, familiar. But this time, every drop would carry a trace of the dead star's final breath. The storm would no longer just be weather. It would be the universe, still falling. Radioisotopes like iron-60 would settle into future rock layers. When a nearby star explodes, it doesn't just send light across the universe. It leaves a fingerprint. Not in the sky, in the rocks beneath our feet. Every supernova creates a blizzard of radioactive dust, tiny atoms forged in the heart of the explosion. These are elements that didn't exist before the star died. Rare, unstable isotopes like iron-60, plutonium-244, and aluminum-26. Each one is a microscopic clue that says a star died nearby, and its ashes reached here. If a supernova went off within a few dozen light years of Earth, some of that dust would eventually drift into our solar system. It would take thousands of years to get here, slowly pushed and guided by magnetic fields and solar winds. But it would arrive, floating through space like invisible pollen, sprinkling down through the atmosphere and settling into the oceans and soil. Once it lands, it becomes part of Earth's next chapter. Iron-60, for instance, has a half-life of about 2.6 million years, meaning it lingers for a long, long time before decaying. It doesn't stay on the surface. Over time, it gets buried, locked inside sediments, coral reefs, and deep-sea crusts. Millions of years later, scientists can dig down, measure it, and say, right here, this is when a nearby star exploded. We've already found that evidence. Samples from the Pacific Ocean, the Indian Ocean, and even Antarctic snow all contain traces of iron-60 that don't come from Earth. They match the signature of a supernova that likely occurred around 2 or 3 million years ago, possibly close enough to affect our climate and ecosystems. Another layer appears from about 7 million years ago, suggesting we've been brushed by dying stars more than once. That means the ground we walk on literally carries cosmic fingerprints, dust from stellar deaths embedded in stone. If another supernova happened near us today, it would leave its own signature for future species to discover. Long after we're gone, when continents have shifted and new life has taken our place, those same isotopes would still be there, faint but measurable. To some distant scientists, 100 million years from now, the layer might look like a thin, radioactive line between epochs. And maybe they'd wonder what happened to the civilization that lived just before it. The beauty of isotopes like iron-60 is that they turn catastrophe into a kind of time capsule. Every atom tells a story of cosmic recycling, a star's core collapsing, exploding, and scattering its elements across space, where they eventually become part of new planets and perhaps new life. So, in a sense, when a supernova dusts Earth with radiation, it's writing a message into our geology. I was here, I burned bright, and I helped make you. Someday, long after the glow fades, the universe's obituary for that star will still be preserved, not in light, not in memory, but in stone. The ionizing pulse could trigger lightning storms planet-wide. It starts with silence, the kind of stillness that makes your skin prickle. Then, out of nowhere, lightning cracks across the sky, not from clouds, but from the air itself. If a nearby star exploded, the flood of energy that reached Earth wouldn't just come as light or radiation. It would arrive as an ionizing pulse, a wave of high-energy photons and particles that tear electrons off atoms in our atmosphere. And when you strip electrons from air molecules, you create the perfect recipe for one of nature's most dramatic shows: lightning. Here's why. Lightning happens because of imbalance. Normally, clouds act like massive electrical batteries. Ice particles bump together. Charges separate, and when the difference between sky and ground gets big enough, the air breaks down and electricity surges through. That's lightning. Now imagine that same imbalance happening everywhere at once. Gamma rays and cosmic particles from a nearby supernova would ionize vast sections of Earth's atmosphere, turning neutral air into a conductive plasma. Electrons would get ripped free, leaving behind charged ions. Suddenly, the entire sky becomes unstable, full of loose energy waiting to connect. The result? A world wrapped in storms. Flashes of lightning could erupt in places that have never seen them before. Deserts, tundras, open oceans. Bolts might jump between layers of the atmosphere instead of striking the ground. The upper sky could flicker like a broken neon sign. It wouldn't be the gentle rumble of a summer thunderstorm. It would be a global electrical symphony, roaring day and night. And unlike normal lightning, these strikes wouldn't need clouds. They'd form in clear air, powered by pure radiation-driven ionization. It would be like the planet itself was trying to discharge the static of a cosmic punch. For days, maybe weeks, Earth's atmosphere would sizzle with electrical activity. The constant lightning would produce its own side effects: nitrogen oxides, ozone, and heat. Ironically, it could temporarily increase ozone levels in some regions, even as other areas lost theirs, a brief, chaotic rebalancing act. The sight would be both terrifying and beautiful. Imagine standing on a mountaintop at night, watching the horizon flash like a strobe, bolts stretching from sky to sky, painting the clouds white and violet. The air would buzz, radio signals would die, and the whole world would sound faintly alive. A low, continuous hum of thunder echoing across continents. Eventually, it would calm. The atmosphere would cool, the free electrons would find homes again, and the skies would go quiet. But the evidence would remain. Scorched soil, strange chemical residues, and perhaps even new atmospheric compounds created in the chaos. Scientists think massive bursts of radiation can indeed spark lightning. It's been observed after nuclear detonations and solar flares. A supernova would have that effect on a global scale. So, if the stars ever decide to unleash their fury nearby, the first sign might not be fire or ash. It might be the sky itself lighting up in protest, a storm that spans the entire planet as Earth discharges the energy of a dying sun. Trees would record radiation spikes in their rings. If a nearby star exploded, not every witness would have eyes to see it. Some would stand silent, rooted in the ground, quietly writing the story of the disaster into their own bodies, one ring at a time. Trees are timekeepers. Every year, they add a new layer of growth beneath their bark, a thin circular ring that captures a snapshot of that year's environment, temperature, rainfall, soil chemistry, even air composition. If you cut a tree open, you can literally read its memories. Now imagine what happens when the sky itself changes. When a supernova goes off close enough to Earth, the flood of radiation and cosmic particles tears into the atmosphere, creating rare isotopes, unusual forms of carbon, beryllium, and chlorine. One of the most important is carbon-14. It forms when cosmic rays strike nitrogen atoms high in the atmosphere, turning them radioactive. Normally, only a tiny amount forms each year, and plants absorb it through carbon dioxide during photosynthesis. But if a nearby star explodes, the amount of cosmic radiation skyrockets, and suddenly so does the amount of carbon-14. Trees would drink that carbon right out of the air, sealing it into the wood of that year's ring. The result? A radiation spike preserved in living wood, a timestamp of the moment the universe briefly touched Earth. We've actually seen this happen before. Tree rings from Japan and Europe show a massive carbon-14 jump around the year 774 CE, a mystery spike so intense it couldn't be explained by normal solar activity. Some scientists believe it may have been caused by a nearby cosmic event, perhaps a small supernova or a powerful gamma-ray burst. Another smaller spike appears around 993 CE. In both cases, the trees remember something the human world barely noticed. If a closer or stronger supernova hit, the pattern would be unmistakable. Every tree on Earth, from rainforest giants to tiny alpine pines, would carry the same radioactive signature. Even centuries later, long after cities eroded and records vanished, future scientists could cut into ancient wood and find the fingerprint of that cosmic blast. It's poetic, really. The light from the explosion might last weeks in the sky, but the echo in tree rings could last for tens of thousands of years. Each forest becomes a living archive, holding a record of how much the planet changed in that instant, how much radiation filtered through the air, how the chemistry of life itself shifted. And if humanity were gone by then, those rings would still tell the story, not through words, but through atoms. A quiet testimony written in wood grain, lines that whisper, "There was a time when the stars burned too bright, and we felt it." A supernova might scorch the sky for a season, but the trees would remember it for eternity.
turning cosmic catastrophe into a natural journal entry, written one ring at a time.
Ancient supernovae left isotope traces in Antarctic ice cores. There's a place on Earth that keeps the universe's secrets, buried under kilometers of frozen silence. It's not a telescope or a satellite or a lab. It's Antarctica. Every year, layer by layer, snow falls on the southern continent, compressing into ice. And that ice doesn't melt away. It stacks, forming frozen pages in a planetary diary that stretches back hundreds of thousands of years. Inside it are trapped bubbles of ancient air, volcanic ash, desert dust, and, astonishingly, traces of exploding stars. When a nearby supernova erupts, it sprays the galaxy with exotic isotopes, rare forms of elements that don't normally exist on Earth. These isotopes drift through space as microscopic dust, moving slowly, carried by interstellar winds until they cross paths with our solar system. Some of that cosmic debris falls through our atmosphere, attaching to snowflakes and becomes locked in ice. And there it waits. Among the isotopes scientists look for, one of the most telling is iron-60, a radioactive version of iron made only in supernovae. It doesn't form in volcanoes, meteorites, or the sun. It can only come from a dying star. Another is plutonium-244, a heavy element so rare it can only be created in violent cosmic events. When scientists drill deep into Antarctic ice cores, they find faint spikes of these isotopes in specific layers, cosmic fingerprints frozen in time. The most famous discovery came in 2021 when researchers studying Antarctic snow found iron-60 atoms less than 20 years old. That means the dust is still falling, remnants from a supernova that happened a few million years ago, still drifting through our corner of the galaxy. We are quite literally passing through the ashes of an ancient explosion right now. Dig deeper into older ice layers and you find echoes of even earlier events. Around 2 to 3 million years ago, there's a stronger signature, suggesting one or more supernovae went off nearby, maybe just 100 light-years away. Some scientists think those explosions may have thinned Earth's ozone layer, cooled the climate, and subtly altered evolution, possibly contributing to the rise of early humans. It's strange to think about. Antarctic ice, so still and white, quietly recording the memory of a distant fire. Each flake of snow falling there might contain a few atoms forged in a long-dead star, atoms that drifted across space for millions of years before coming to rest on our planet. Those isotopes are tiny, almost unmeasurable. A few atoms among quadrillions, yet they tell a story far larger than we can see. A story of death and creation, of stars exploding so far away they're invisible to the naked eye, yet close enough for their dust to land on our doorstep. So when scientists melt those ice cores and peer at the faint traces of iron-60 and plutonium-244, they're not just studying chemistry, they're reading cosmic history, proof that the universe has reached out and touched Earth before. And it will again. Earth's magnetic poles might flip faster due to field disruption. Imagine waking up one morning to find that compasses no longer point north. They point somewhere else. And in a few decades, maybe even years, North and south switch places entirely. That sounds like science fiction, but it's something Earth has done before, many times. It's called a geomagnetic reversal, and it's part of the planet's natural rhythm. The magnetic field that protects us isn't fixed, it's constantly shifting, generated by molten metal churning deep inside the planet's core. But here's the twist. If a nearby star exploded, that rhythm could go completely off beat. A supernova doesn't just release light and radiation. It floods space with charged particles. These particles can distort magnetic fields, compress the heliosphere, and even affect how energy flows through our atmosphere. If enough of them hit Earth, they could temporarily weaken or destabilize the planet's own magnetic field. Our magnetic field works like a giant bar magnet, created by the motion of molten iron and nickel in the outer core, what scientists call the geodynamo. That flow is delicate. It depends on temperature, rotation, and subtle interactions between core and mantle. When cosmic radiation bombards the planet, it can cause small but significant changes in the energy balance of our upper atmosphere and magnetosphere. Those changes ripple downward, altering how the magnetic field behaves. Normally, magnetic reversals take thousands of years to happen. The last one, the Bruns-Matuyama reversal, occurred about 780,000 years ago. But the magnetic field has been acting unstable lately. It's weakening faster than usual, and the North Pole has been drifting towards Siberia at more than 50 kilometers per year. Add a cosmic shock wave from a nearby supernova, and that drift could accelerate dramatically. It wouldn't flip overnight, but the poles could start wandering wildly. The field lines might tangle, fragment, or even split into multiple mini-poles before settling into a new configuration. During that chaos, Earth's magnetic shield would weaken, meaning more cosmic radiation, more auroras at lower latitudes, and more damage to satellites and power grids. If you lived through it, you wouldn't see the flip happen directly. The sky wouldn't change color, and your phone's compass would just seem confused. But over decades, navigation systems would have to constantly update, and migratory animals, whales, birds, and sea turtles would lose their magnetic sense of direction. Geological records show that the last time Earth's field weakened dramatically, radiation levels on the surface rose, ozone thinned, and climate patterns may have shifted. Now imagine that same natural process being kick-started by a supernova's charged particle wave, a cosmic nudge that speeds up the inevitable. The scary part is that magnetic reversals don't destroy the planet. They just expose it. With a weakened field, more solar and cosmic radiation would reach the surface, adding stress to an already wounded biosphere. So if the stars ever decide to die close enough, their final act might not just light up our sky. It might make Earth's compass spin faster, turning magnetic north into a moving target. And somewhere in the distant future, geologists studying that magnetic chaos in ancient rock will realize that was the moment the universe reached into our core and twisted it. Deep ocean microbes could survive while surface life collapses. When a nearby star explodes, the first thing to die would be sunlight. The sky would turn dangerous, filled with ultraviolet radiation, stripped ozone, acid rain, and cosmic rays bombarding the surface. Forests would wither, crops would fail, and oceans would boil with chemical change. The upper world, everything we can see, would start to die. But deep below, in the silent blackness of the ocean floor, life would barely notice. Far beneath the waves, kilometers down, exist entire ecosystems that have never seen the sun. These are the deep ocean microbes, life forms that feed not on light, but on chemistry. They live near hydrothermal vents, where water heated by the planet's molten core gushes out rich in minerals. Around these vents grow alien-looking forests of tube worms, crabs, and bacteria that thrive in total darkness. To them, the death of the sky means nothing. If a supernova blasted Earth with radiation, it would sterilize much of the surface and upper ocean. UV light and cosmic rays would shred DNA and destroy plankton, a base of the marine food chain. Without plankton, everything above starves. But those deep-sea microbes would keep feeding on hydrogen sulfide, methane, and iron, quietly thriving while the rest of the biosphere collapses. In fact, scientists believe they've done it before. During Earth's great mass extinctions, like the Permian-Triassic event 252 million years ago, when nearly all complex life died out, deep ocean microbes kept going. Some of their chemical traces still appear in rock layers today. Even when the surface becomes unlivable, the deep ocean stays relatively stable. Constant temperature, no sunlight, and layers of water shielding it from radiation. If a nearby supernova hit, those microbes would be our planet's last survivors. They'd endure the radiation, the chemical chaos, even the acidification of seawater. Over millions of years, as the skies cleared and the radiation faded, they could slowly repopulate the oceans, giving rise to new species. Life would begin again, not from forests or coral reefs, but from microscopic survivors in the darkest corners of the planet. It's humbling, isn't it? The idea that if a cosmic catastrophe wiped us out, the planet wouldn't be empty. It would still be breathing, quietly, miles below the surface. Scientists sometimes call these deep ecosystems time capsules of early Earth because they resemble the first life that ever appeared. Heat-loving, chemical-eating microbes that might have thrived 4 billion years ago when the planet itself was toxic and chaotic. In a way, they're not just survivors, they're reminders of what life truly is. Resilient, stubborn, and endlessly patient. So, even if a star's explosion turned Earth into a scorched wasteland, the story of life wouldn't end. It would just retreat into the dark, biding its time, waiting for the world above to calm down. And when the dust settled, when the radiation faded and the oceans cooled, life would climb back up from the deep, carrying with it the memory of a dead star and the proof that even the universe's worst fire can't burn everything away. UV exposure would sterilize large parts of the biosphere. The sun gives life, but it also has the power to erase it. Normally, we're protected from that danger by the ozone layer, Earth's invisible sunscreen. But if a nearby star exploded, that shield could vanish almost overnight. And without it, sunlight would turn deadly. When a supernova hits Earth with gamma rays, it tears apart nitrogen and oxygen in our upper atmosphere, creating nitric oxide and destroying ozone. That single reaction opens the door for ultraviolet radiation, the most aggressive part of sunlight, to pour through unfiltered. And UV light doesn't burn slowly like infrared. It slices through living cells like a scalpel. At the surface, the effect would be catastrophic. UV radiation can break chemical bonds in DNA, causing mutations that stop cells from dividing. In large doses, it doesn't just cause cancer, it kills outright. Proteins unravel, cell walls disintegrate, and delicate structures like chloroplasts in plants are destroyed. The first victims would be microscopic. Ocean plankton, the foundation of the food web, would be obliterated within days in the upper layers of water. Without them, fish and whales would starve. Coral reefs would bleach faster than they already do under climate change, turning ghost white as the algae that feed them die off. On land, crops would wilt. Leaves would show white burns where sunlight hit directly. Forest canopies would thin. Animals that depend on those plants, from insects to grazing mammals, would begin to starve. And the damage wouldn't stop with death, it would stop birth. UV light sterilizes. It damages reproductive cells in plants and animals alike. Seeds would fail to sprout. Eggs would stop developing. Entire ecosystems would lose their ability to regenerate. That's what scientists mean when they say UV exposure would sterilize large parts of the biosphere. It wouldn't look like fire or ash. It would be quiet, a soft apocalypse of light. The world would still look beautiful at first. Blue skies, bright oceans, golden sunlight. But life beneath that brilliance would fade, as though bleached out of existence. Even bacteria on the surface would struggle. Only a few radiation-resistant species, like Deinococcus radiodurans, nicknamed Conan the bacterium, might survive, clinging to shaded rocks or burrowing into the soil. Deep sea and underground life would carry on, but the surface would go eerily still. We have hints this may have happened before. Around 440 million years ago, during the Ordovician extinction, almost all marine species vanished in a geologically short time. One theory is that a nearby gamma-ray burst or supernova stripped Earth's ozone, letting UV light sterilize the oceans. It's a chilling thought that something so simple, so ordinary as sunlight, could turn into a planet-wide weapon. No explosions, no burning cities, just the same golden light we see every day, but suddenly, catastrophically, too pure. The very glow that makes our world alive would instead make it silent. Whales and deep-sea creatures might inherit the planet temporarily. When a nearby star explodes, sunlight stops being gentle. Radiation floods the surface. Ozone crumbles, and ultraviolet light turns the upper world into a sterilizing oven. Forests crisp. Plankton die, crops fail, and the skin of every exposed creature burns under skies that look perfectly normal. But far below the reach of that deadly light, a different world waits, cold, dark, and ancient. The deep ocean. Miles beneath the surface, sunlight never arrives. The water there is black, pressurized and eternal, a place so far removed from the surface that it could almost be another planet. Life there doesn't depend on warmth from above. It feeds on drifting marine snow, flakes of dead plankton, fish, and waste falling from the layers of life that once thrived in the light. If a supernova sterilized the surface, the deep ocean would barely flinch. The whales, with their immense lungs and slow metabolism, could retreat deeper and stay there for weeks. Some species, like sperm whales and Cuvier's beaked whales, already dive thousands of meters into the dark to hunt. Their thick layers of blubber shield them from temperature swings and even a bit of radiation. As long as they could find food, they might survive long after most land animals were gone. Around them, deep-sea creatures, anglerfish, giant isopods, snailfish, and microbial colonies near hydrothermal vents would continue their quiet routines. The vents spew heat and chemicals from Earth's mantle, fueling ecosystems that don't need the sun at all. To these organisms, a sterilized surface wouldn't mean apocalypse, just a quieter snowfall of nutrients drifting down from above. For a time, maybe centuries, they'd be Earth's dominant life. Picture a world where humanity and every land creature is gone, but the oceans still whisper with life. A pod of whales singing in the darkness, their voices echoing through black water. Bioluminescent fish pulsing with soft blue light. Shrimp, worms, and bacteria feeding on chemical heat from the seafloor. The world would seem dead from space, yet still alive in its deepest veins. Eventually, even that kingdom would feel the change. Without new organic material falling from above, the deep ocean would slowly starve. But not before leaving behind survivors. Hardy bacteria and archaea that could cling to rocks, digest minerals, and wait for the planet to heal. In that sense, the deep sea is Earth's emergency backup, a biological vault. Whenever catastrophe hits the surface, asteroid, ice age, or cosmic blast, the deep ocean hides life long enough for it to restart later. So if a nearby supernova ever sterilized the surface, the planet wouldn't truly die. It would simply hand the keys to the deep. Whales would sing to an empty world. Microbes would quietly persist, inheriting Earth not with fire or technology, but with patience. And when the skies finally cleared centuries later, it would be their descendants, not ours, who would rise to repopulate the blue planet. Skin cancers in humans and animals would skyrocket. It wouldn't happen all at once. No explosion, no flash, no smoke, just sunlight, the same warm light that's been comforting life for billions of years, quietly turning into a killer. If a nearby star exploded, Earth's ozone layer would take a catastrophic hit. That thin veil of gas high above us is what filters out ultraviolet, UV radiation, the invisible, high-energy light that damages DNA. Normally, only a small fraction of UV reaches the ground. But after a supernova, the flood of gamma rays and cosmic particles would shred the ozone apart, letting ultraviolet light pour through unfiltered. And that's when the real pain begins. Ultraviolet radiation doesn't just tan the skin, it mutates it. Each beam is a packet of energy that strikes DNA like a hammer, snapping molecular bonds and scrambling the genetic code inside living cells. Most of the time, your body's repair systems catch those mistakes. But when exposure increases dramatically, those systems get overwhelmed. Cells start replicating with errors, and that's what cancer is. Cells that forgot how to stop growing. In a post-supernova world, skin cancer rates would explode. First, you'd see it in the animals.
Grazing species, deer, cattle, kangaroos, would develop raw patches and sores where their fur or skin is thinnest. Birds would lose feathers and show lesions around their beaks and legs. Even marine creatures that surface often, like dolphins and whales, would suffer burns and tumors on their backs where sunlight strikes the water. For humans, it would be relentless. The usual precautions, sunscreen, shade, clothing, wouldn't be enough. Ordinary sunlight could burn the skin in minutes. Outdoor work would become dangerous. Children would have to play under UV-filtered domes. Even cloudy days would be no refuge. UV light passes straight through clouds. And it's not just the skin. UV light also damages eyes. Cataracts, corneal burns, and blindness would surge across all species. Insects whose delicate wings and eyes evolved under our current level of sunlight would start dying off. Food webs would collapse not because of famine or cold, but because the light itself became too strong. Over time, life would adapt, a little. Populations that survive might evolve thicker skin, darker pigmentation, or more efficient DNA repair mechanisms. But evolution takes generations. In the meantime, much of the biosphere would be in crisis. The irony is that the culprit, sunlight, would still look normal. The sky would stay blue, the days bright, but the air above would have lost its invisible shield, and every sunrise would deliver a dose of radiation strong enough to break life's most fundamental code. It's a quiet apocalypse. No fire, no noise, just light that kills. And long after the supernova's glow fades from the night sky, its true legacy would linger, in every cell struggling to fix its DNA, in every scar, in every tumor. A reminder that even the friendliest star can turn deadly when the universe decides to pull back its protection.
Photosynthesis collapse triggers global food chain failure. The green color of a leaf might be the most underrated miracle in the universe. It's more than decoration, it's a survival engine. Through photosynthesis, plants use sunlight to convert carbon dioxide and water into oxygen and food. Every breath you take, every bite you eat can be traced back to that quiet chemical trick happening in green cells across the planet. Now imagine that system shutting down. When a nearby star explodes, Earth's ozone layer gets stripped away and ultraviolet radiation floods the surface. That radiation doesn't just burn skin, it destroys chlorophyll, the pigment that lets plants absorb sunlight. When chlorophyll breaks down, photosynthesis stops. Without photosynthesis, the whole planet's food chain collapses. It starts invisibly, leaves fading faster than usual, crops growing slower, forests taking on a dull, sickly tone. Then the effects cascade. Without healthy plants, there's less oxygen production, less carbon capture, and less food for herbivores. Insects lose their feeding grounds. Grazing animals starve. Predators follow soon after. The oceans would fare even worse. The base of marine life isn't fish or coral, it's phytoplankton, microscopic plants floating near the surface. They make half of Earth's oxygen and feed nearly everything that swims. But they're extremely sensitive to UV light. Even a moderate increase in radiation can kill entire populations.
A supernova's radiation could sterilize the upper layers of the ocean, erasing plankton for thousands of miles. Without plankton, fish die. Without fish, seabirds and whales starve. The blue world turns silent. Within months, the planet's carbon cycle, the balance between life, air, and water, would fall apart. Carbon dioxide would build up, oxygen levels would drop, and climate systems would spiral unpredictably. Deserts would expand, rainfall patterns would shift. Even surviving plants would struggle, their damaged cells unable to absorb enough sunlight without burning. Humans, of course, depend on all of this. No crops, no livestock, no seafood. Even if people hid underground or under domes, the food sources outside would vanish. Supply chains would break. Famine would spread faster than war ever could. But it's not just about hunger, it's about the end of balance. Photosynthesis is what makes life self-sustaining. Without it, every species, from worms to whales, becomes a consumer without a producer. The system runs out of energy, and everything that depends on sunlight becomes debt in nature's economy. And yet, not everything would die. Some bacteria, deep in the soil or around volcanic vents, could still survive, feeding on minerals instead of light. They'd become the planet's new green, microscopic, hidden, patient. Over millennia, they could give rise to new ecosystems. So when scientists say a supernova could trigger food chain collapse, they don't mean a few bad harvests. They mean the end of sunlight as nourishment. For billions of years, plants have turned starlight into life. If a nearby star explodes, that ancient partnership ends. The light still shines, but it stops feeding the world. The same sun that made us grow would rise on an earth that no longer knows how to eat. Insects might survive longer than mammals due to exoskeletal shielding. If a nearby star exploded, the first thing to die would be the big things, the warm, soft, fragile creatures that rule the surface. Humans, birds, mammals. We'd all struggle to survive in a world filled with ultraviolet radiation, poisoned air, and failing ecosystems. But while our species faded under the harsh new sun, something far smaller and much tougher might carry on. Insects. It sounds almost poetic. The planet wiped clean of its giants, yet buzzing faintly with the survivors we usually swat away. Here's why they'd make it when we wouldn't. Insects wear their skeletons on the outside. Their exoskeleton, a tough shell made of chitin, acts like natural armor. It's lightweight but dense, shielding their organs from radiation, dehydration, and even acid. That same armor that protects them from predators and weather might also help them resist the ultraviolet onslaught after a supernova. When the ozone layer vanishes and UV rays pour down unchecked, mammals, with thin, exposed skin, burn, mutate, and die. But many insects are already adapted to sunlight and dryness. Beetles, ants, and cockroaches have glossy, pigmented shells that reflect radiation. Their small size means less surface area to absorb damage. And because they reproduce so quickly, even heavy losses can be replaced in days or weeks. Where mammals need complex ecosystems, plants, shade, food chains, insects need very little. Some can eat rotting matter, fungi, or even each other. Others can survive months in suspended animation, sealed underground or inside cocoons. A global catastrophe that wipes out 90% of life might just thin their numbers, not end them. And radiation? Many species have already proven surprisingly resistant. Cockroaches, fruit flies, and certain beetles can endure doses of radiation far beyond what would kill a human. Their cells repair DNA differently, faster, more efficiently, less prone to cancers that plague larger animals. If the surface world turned toxic, insects could retreat underground or into cracks in the soil, hibernating through the worst of it. Termites could live off decaying wood, shielded by dirt. Ant colonies deep in their tunnels might never even know the apocalypse happened above. Over time, as the radiation faded and plants slowly regrew, insects would emerge again, scarred but alive, ready to reclaim the world. The forests might be gone, but the decomposers would remain, breaking down the ruins of what once was. It's ironic. Mammals, the pinnacle of evolution, would vanish. But the buzzing, crawling, stubborn creatures we spend our lives trying to kill, mosquitoes, beetles, flies, would write the next chapter of Earth's story. In a world where sunlight has turned lethal, intelligence and technology might mean nothing. Survival would belong to whoever could hide, harden, and hatch. And that's the insect kingdom, small, ancient, and built for the apocalypse. So if a star ever explodes nearby and ends the age of mammals, the Earth wouldn't be silent. It would hum, softly, persistently, with the sound of wings still beating in the ruins. Supernova shockwaves compress nearby gas clouds, birthing new stars. A supernova is an ending, a star's final scream before fading into dust. But in the grand design of the universe, endings aren't really endings, they're beginnings in disguise. When a massive star explodes, the blast doesn't just scatter debris, it sends a shock wave, a wall of high-energy gas and radiation traveling through space at thousands of kilometers per second. As it expands, it plows into the cold, dark molecular clouds floating between stars, the raw material of the cosmos. These clouds are vast, so big they can stretch for dozens of light years, made mostly of hydrogen and helium, with a sprinkle of cosmic dust. Normally, they just drift in silence, too diffuse to form anything on their own. But when a supernova's shock wave slams into one, everything changes. The pressure from that wave squeezes the gas, forcing atoms closer together. Gravity, suddenly given a head start, takes over. The densest parts of the cloud collapse inward, heating up until nuclear fusion ignites. And just like that, new stars are born. A dying star in its final act becomes the midwife for the next generation. It's one of the most beautiful paradoxes in astrophysics, destruction creating creation. The energy that ends one life becomes the spark for dozens more. Some of the brightest clusters of young stars in our galaxy, like the Orion Nebula, were likely sculpted by supernova shockwaves millions of years ago. Even our own sun might be the child of such an event. Scientists studying isotopes in meteorites have found traces of iron-60, an element only made in supernovae, suggesting that our solar system formed from gas enriched and compressed by a nearby stellar explosion. So every atom in your body, every breath you take, every beam of sunlight hitting your skin may owe its existence to a star that died long before Earth was born. If you could watch the process unfold in deep space, it would look like a slow-motion ballet. The shock wave rolls through a dark nebula, igniting waves of color. Pink hydrogen gas glowing, blue starlight scattering through dust, and bright new stars flickering to life like embers catching in ash. It's the universe's version of regeneration, chaos reshaping itself into order again. This process is so common that galaxies themselves recycle their stars endlessly. Each generation ends in fire, and from those ashes comes the next. The cosmos, it turns out, runs on renewal. So when you see a picture of a supernova remnant, a glowing ring or cloud in some distant galaxy, you're not just looking at destruction. You're looking at the seedbed of creation, a nursery forged by violence. Every new sun that lights the sky owes its life to one that died before Earth was born. And somewhere out there, even now, a supernova shockwave is passing through a cold cloud, squeezing it, shaping it, and setting off the chain reaction that will one day give birth to another world, another sky, and maybe, just maybe, another version of us.
The explosion could trigger comet showers from the Oort cloud. Far beyond the planets, past Pluto, past the Kuiper belt, past everything we've ever seen, lies the edge of our solar system. A vast, dark sphere filled with billions of icy bodies, each no bigger than a mountain. It's called the Oort cloud, and it's our cosmic attic, full of frozen leftovers from the dawn of the solar system. Most of the time, it's quiet there. The comets drift silently, orbiting the sun once every few million years, untouched and unseen. But if a nearby star explodes, a supernova, within a few dozen light years, that peaceful silence ends. A supernova doesn't just send light and radiation, it sends a shock wave, a physical wall of expanding gas and particles moving thousands of kilometers per second. When that wave reaches our solar system, even after thousands of years, it still carries enough energy to rattle the edges of the Oort cloud. The icy bodies out there are barely held in place by the sun's gravity. They're fragile captives, and a passing shock wave, or even the gravitational ripple from the explosion, could be enough to knock thousands of them loose. Those displaced comets would start falling inward, pulled by the sun's gravity toward the inner solar system. Some would slingshot around harmlessly, but others would head straight for us. It wouldn't happen all at once. The first few might arrive tens of thousands of years after the explosion. But once it started, it could go on for millennia. A slow rain of icy missiles from the outer dark. Astronomers have a name for this kind of cosmic event, a comet shower. And there's evidence it has happened before. Geological records suggest that periodic bursts of comet impacts may line up with nearby supernovae
or passing stars disturbing the Oort cloud. The craters they leave on the Moon, Mars, and Earth might be silent reminders of ancient explosions light years away. If it happened again, it would be beautiful and terrifying. For thousands of nights the sky would blaze with new comets, long tails stretching across the heavens, dozens visible at once. To ancient humans, it would look like prophecy. To us, it would look like the universe throwing stones. Most would burn harmlessly in the atmosphere, but a few big ones could hit hard. Even a single 10-kilometer-wide comet could release energy equal to millions of nuclear bombs, enough to trigger tsunamis, wildfires, or global cooling from dust clouds. It would be a delayed aftershock of the original supernova, destruction arriving long after the flash had faded. And yet, this too fits the pattern of the universe, creation and chaos feeding each other. The same explosion that might sterilize one world could spark new chemistry on another, comets delivering water, carbon, and organic molecules to young planets. So when a star dies, it doesn't just end its own story, it tosses new chapters into the galaxy. A single explosion could turn our solar system into a pinball machine, comets blazing across the sky for generations, messengers of a death that happened light years away.
Interstellar dust might dim the sun slightly for centuries. If a nearby star exploded, its light would be the first thing we'd see, a sudden brilliant point in the sky, brighter than the moon. But long after that brightness faded, something quieter would follow. Not fire, not radiation, dust. When a star goes supernova, it doesn't just vanish in light. It throws its body into space. Heavy elements like carbon, silicon, and iron are blasted outward, forming interstellar dust, tiny particles smaller than smoke, drifting across the void for thousands of years. Eventually, some of that dust would reach us. Our solar system isn't sealed off. It floats through the Milky Way like a ship through a sea of gas and particles. The sun's magnetic bubble, the heliosphere, normally keeps most cosmic dust away from us. But if a supernova exploded close enough, say within 30 or 50 light years, its shock wave could compress that bubble, letting dust slip through. Over centuries, more and more of it would drift inward. These particles would scatter sunlight, just like haze in our atmosphere scatters daylight after a volcanic eruption. The effect wouldn't be dramatic, no sudden darkness, no eclipse, but subtle and global. The sky might look a little duller, the sunlight a little softer. Daytime would take on a faintly muted tone, as though the world was always a few minutes before sunset. Scientists estimate that if enough supernova dust entered our solar system, solar radiation at Earth's surface could drop by a few %. That's enough to cool the planet slightly, shift climate patterns, and alter growing seasons. Not an ice age, but a quiet chill that could last for centuries. We might not even notice at first. Crops would take a little longer to grow. Winters might stretch a bit longer. Sunsets might seem more colorful, redder, richer, because dust scatters blue light away. But over generations, those small differences would add up.
And that dust wouldn't just float between planets, it would fall. Some would burn up in our atmosphere, streaking as faint, slow meteors. Some would settle into the oceans and soils, adding rare isotopes like iron-60 and plutonium-244, the unmistakable fingerprints of a supernova. We've already found that dust in the Earth's crust, traces from explosions that happened 2 or 3 million years ago. It's how scientists know that our planet once passed through the debris of dying stars. So if it happened again, the sun would still shine, but just a little dimmer. The daylight would feel different, like the entire world was under a faint ancient veil. And every breath you took, every handful of soil, every snowflake that fell, would contain atoms from that distant death. The irony is beautiful, a dead star's dust blocking our sunlight, even as it sprinkles the elements that one day form new worlds, new skies, and new suns. The brightness of the universe is never constant. It breathes, it burns, it dims, it dusts itself. And through it all, we orbit quietly, spinning through the ashes of stars that refuse to be forgotten. Magnetic turbulence could disrupt cosmic ray trajectories for millennia. When a star explodes, the light is the most obvious thing. That brilliant flash across the heavens. But what you don't see is the chaos it leaves behind, invisible, sprawling, and violent. That chaos is magnetic turbulence, and it can reshape the flow of energy through an entire corner of the galaxy for thousands of years. Here's what happens. When a supernova goes off, its explosion tears through space at tens of thousands of kilometers per second, dragging magnetic fields with it. Space isn't empty. It's threaded with magnetic lines like invisible spiderwebs, delicate but everywhere. The shockwave twists and shreds those lines, turning smooth fields into snarled tangles of magnetism. It's as if the universe's electrical wiring suddenly got yanked apart. Through those same magnetic highways travel cosmic rays, high-energy particles, mostly protons and atomic nuclei, zipping through space at nearly the speed of light. Normally, they follow the galaxy's magnetic structure, winding gently through the spiral arms like cars following invisible lanes. But when a supernova detonates nearby, those lanes turn into a maze. The shockwave stirs magnetic fields so violently that cosmic rays begin scattering in every direction. Some are trapped near the explosion site for thousands of years, bouncing back and forth inside tangled fields like marbles in a storm drain. Others are redirected entirely, bent, deflected, or delayed by centuries. The result is a galactic fog of radiation, diffused and unpredictable. If Earth sits anywhere near that disturbed region, the effect would be profound. The normal, steady drizzle of cosmic rays we experience would fluctuate wildly. One century might bring higher doses, another might bring less. That radiation imbalance could affect atmospheric chemistry, cloud formation, even the mutation rates of living organisms. The chaos doesn't fade quickly. Space, on this scale, is sticky. Turbulence takes millennia to smooth out. Even after the visible supernova remnant fades, the magnetic scars it leaves behind ripple through the interstellar medium for eons. It's like stirring dye into water. Long after the initial swirl, the color still lingers. Astronomers studying the remnants of ancient supernovae, like the Vela and Cygnus Loop nebulae, can still detect magnetic fields thousands of light-years wide. Those remnants continue to bend cosmic rays today, long after the original star's light faded from view. In fact, scientists think the strange variations in cosmic ray intensity Earth has recorded over geological time, found in tree rings, ice cores, and rock isotopes, might be echoes of ancient magnetic turbulence from long-dead stars. So even when the supernova itself is forgotten, its magnetic fingerprint remains, reshaping the flow of energy through space for generations of stars and planets to come. The explosion ends in seconds. The light fades in years. But the magnetic storm it leaves behind? That can last longer than human civilization. A ghost field, swirling endlessly, carrying the memory of a single dying sun.
Gravitational waves would ripple faintly through space-time. When a star dies in a supernova, the blast is so powerful, it doesn't just light up the universe, it shakes the fabric of reality itself. Literally. Physicists call those shakes gravitational waves, faint ripples that travel through space-time, the invisible fabric that everything in the universe rests on. To understand them, imagine the universe as a giant, flexible sheet. When something massive moves suddenly, a black hole merging, a neutron star collapsing, or a star exploding, that sheet quivers. The waves race outward in every direction, stretching and squeezing space itself as they go. A nearby supernova would send out one of those waves, not strong enough to tear the cosmos apart, but enough to ripple through everything, even through you, right now. If you were floating in space when it arrived, you wouldn't feel it. There'd be no shaking, no flash of light. But on a cosmic scale, it's dramatic. Distances between objects literally oscillate. One moment, the space between Earth and the Moon might shrink by the width of an atom, then expand again in a fraction of a second. These ripples travel at the speed of light, crossing galaxies effortlessly. They're unbelievably weak by the time they reach us, but not invisible. We've learned to detect them. In 2015, the LIGO Observatory recorded gravitational waves for the first time, caused by two black holes colliding over 1 billion light-years away. The signal was smaller than the width of a proton, yet it confirmed one of Einstein's wildest predictions. A nearby supernova, though, would be different. The collapsing core of the dying star, a sphere of iron imploding faster than bullets, would send out its own unique pattern of waves. For physicists, it would be a message written in gravity, carrying details about how the explosion began, how fast the core spun, even whether it formed a neutron star or a black hole. For the rest of us, it would be a silent, invisible moment, the universe breathing. These waves don't stop when the light fades. They keep traveling forever, stretching through galaxies, through stars, through planets, through time itself. Long after the explosion, the waves from that one dying star would still be moving outward, faint but eternal. Some scientists think that Earth has been washed by countless such waves since the dawn of life. We never noticed.
They pass through us like wind through glass, bending us ever so slightly, whispering the story of every cosmic catastrophe that ever was. If a nearby star exploded today, LIGO and its successors would hear it first, a faint chirp in the detectors, the sound of space-time itself ringing like a bell. You wouldn't feel it, and you wouldn't see it, but for one brief moment the universe would tremble, and everything, everywhere, would move together. A dying star would make all of existence quiver in sympathy.
Power grids would collapse from geomagnetic surges. When a nearby star explodes, the danger doesn't just come from light or radiation. It comes from something far sneakier: electricity. Not the kind you use to charge your phone, but the kind that flows invisibly through the entire planet when space itself gets angry. Here's what happens. A supernova sends out a wave of charged particles and high-energy radiation that can slam into Earth's magnetic field. Normally, that field protects us. It bends most of the particles away, forming beautiful auroras near the poles. But when the incoming wave is powerful enough, the magnetic field itself begins to buckle and twist. Those twists create electrical currents, enormous ones, that flow through the upper atmosphere and eventually into the ground. This is called a geomagnetic storm, and it can turn the entire Earth into one gigantic circuit. The result? Power grids everywhere start to short-circuit. Transmission lines, the long metal veins that carry electricity across continents, act like antennas, soaking up that geomagnetic energy. Transformers, designed for precise voltages, suddenly face surges hundreds of times higher than normal. Their cores overheat, insulation melts, and in seconds, entire networks can burn out. In 1989, a single solar storm, just from our sun, blacked out the entire Canadian province of Quebec in 90 seconds. Imagine a supernova's blast, magnitude stronger, shaking the magnetic field of the entire planet. The collapse would be instant and global. Cities would plunge into darkness. Communication satellites would fail as radiation fried their circuits, and the loss of synchronization between power systems would ripple like dominoes. Airplanes would lose navigation, hospitals would lose power. Data centers, the digital hearts of our civilization, would go silent. Backup generators might hold for a while, but the damage to transformers and substations would take months, even years to repair. Modern grids depend on precision, and a single geomagnetic surge could turn that precision into chaos. Scientists have modeled what might happen in an event like this. Even a moderate radiation burst could induce electric currents of up to 100 volts per kilometer in long transmission lines. That might not sound like much, but when stretched across a nation's power grid, it's enough to overload everything. And here's the eerie part. The surge would come before the visible light from the supernova even arrived. Radiation travels faster through the interstellar medium than shock waves or debris. By the time the star's death light reached our eyes, the damage would already be done. The world would light up and then go dark. In that silence, the night sky would glow with auroras as far south as the equator, brilliant curtains of red and green rippling where cities used to shine. It would be beautiful and utterly useless.
We built our civilization on electricity, and yet one burst of cosmic magnetism could erase it. It's humbling to think that a star dying light years away could reach across space and flick a switch, and the entire planet would go offline.
Communication satellites would be destroyed. Before you saw the light of a nearby star exploding, before the news reached Earth, before anyone could even react, our link to the modern world would already be gone. Not gradually, instantly. The explosion's first assault wouldn't come in the form of visible light or degree. It would come as a blast of gamma rays and high-energy particles racing across space at the speed of light. When that radiation hit Earth, the first things in its path would be our satellites. Thousands of delicate machines orbiting silently above us, keeping civilization connected. Each of those satellites, from GPS and weather trackers to internet constellations and broadcast relays, depends on microelectronics so sensitive they can be damaged by a single charged particle. Normally, Earth's magnetic field and the satellite's thin aluminum shells provide enough protection, but a nearby supernova would overwhelm those defenses in seconds. Gamma rays would slice through their casings like X-rays through glass, ionizing circuits, erasing memory, and frying processors. Solar panels would be hit by bursts of charged particles that degrade their surfaces, killing power instantly. Communication dishes would stop transmitting. Navigation signals would vanish. From Earth, it would feel like the world suddenly forgot how to talk. Air traffic control systems would lose satellite navigation. Cargo ships crossing oceans would drift off course. Bank networks, timing systems, internet relays, all synchronized by orbiting clocks, would fall out of sync. Within minutes, stock exchanges, communication grids, and navigation services would freeze. And it wouldn't just be the satellites we use every day. Military systems, spy satellites, missile detection networks, and encrypted communication arrays would fail too. Nations would suddenly be blind to each other. A single cosmic event could erase the technological balance of the entire planet. Even the International Space Station wouldn't be safe. Its shielding might protect astronauts for a few moments, but prolonged exposure would fry instruments, sensors, and external panels. They'd be forced to retreat into the most protected modules and hope the radiation storm passed quickly, if they had warning at all. The irony is chilling. A star dying light years away could end the age of instant communication in less than a heartbeat. Astronomers know this vulnerability well. Even moderate solar storms, tiny compared to a supernova's blast, have disrupted satellites and radio signals. In 2003, a solar flare knocked out satellites and disabled GPS systems across parts of the world. A supernova's radiation would make that look like static on a radio. Once the damage was done, rebuilding would take years. We'd have to launch new satellites into an environment still buzzing with residual radiation, all while operating blind. For the first time in decades, Earth would go silent. No GPS, no weather updates, no global internet. Just us and the stars. A dying star's light would appear in the sky, bright, beautiful, impossible to ignore. And somewhere down here, billions of people would stare at it,
not realizing it was the reason their phones, their networks, their entire digital civilization had just gone dark. The universe doesn't need war or invasion to end our communication. It just needs to whisper one time in gamma rays.
GPS would fail worldwide within seconds. Imagine the world going blind, not because the lights went out, but because we lost our sense of direction. Every second of every day, billions of devices quietly talk to the sky. Phones, planes, ships, tractors, delivery trucks, missiles, all listening for signals from a network of satellites orbiting 20,000 kilometers above Earth. That network is the Global Positioning System, or GPS, and if a nearby star exploded, it would vanish almost instantly. When a supernova erupts, it floods space with gamma rays, X-rays, and high-energy particles, all moving at the speed of light. Those waves would reach Earth long before anyone even realized what had happened. The first thing they'd hit would be our satellite network, the fragile backbone of our global navigation system. GPS satellites rely on atomic clocks so precise that a billionth of a second's error can mean meters of inaccuracy. But those clocks and the microchips that read them are extremely sensitive to radiation. A single energetic particle from space can flip a bit in their memory, scramble timing data, or fry a circuit completely. A supernova's gamma-ray pulse would unleash billions of those particles across the entire planet. Within seconds, satellites would glitch, lose sync, and fall out of coordination with each other. The system would collapse in a chain reaction, not because of explosions, but because time itself, the thing GPS depends on, would no longer agree. Down on Earth, the effects would be instant and terrifyingly quiet. Airplanes mid-flight would lose their position data. Ships crossing the ocean would suddenly have no idea where they were. Cars, delivery drones, and rescue teams that rely on navigation software would be stranded or lost. Even things that don't seem connected to GPS, bank transactions, internet routing, power grids would fail, because they all depend on GPS timing signals to stay synchronized. The invisible web that keeps modern civilization running would unravel in seconds. And there would be no quick fix. Restoring GPS isn't just about turning satellites back on. It requires stable timing, orbital recalibration, and coordination between hundreds of ground stations. But with the sky full of residual radiation and fried electronics, launching replacements would be impossible for years. Astronomers have long worried about this vulnerability. Even a powerful solar flare could knock out parts of the GPS system. But a supernova nearby would deliver radiation thousands of times stronger. Every orbiting satellite would be effectively cooked before the first emergency alert could even be sent. The eerie part is how it would feel. No explosions, no warning sirens, just silence, your phone map freezing, airplanes circling, shipping routes stalling, cities flickering as systems fall out of sync. A species that learned to navigate by the stars would be lost again, this time
not because the stars disappeared, but because one of them died. GPS made us masters of precision. A supernova would remind us how fragile that mastery is. One burst of light, and the whole world forgets where it is.
Nuclear power plants would go into emergency shutdowns. If a nearby star exploded, the disaster wouldn't arrive like a firestorm. It would come as an invisible wave, a pulse of radiation, magnetism, and electric chaos racing across space at the speed of light. And one of the first places to feel it would be the beating hearts of our modern world, nuclear power plants. Right now, there are over 400 nuclear reactors operating across the planet, each one a controlled star in miniature, splitting atoms, releasing energy, and running on precision so delicate it depends on stable electricity, communication, and cooling. A nearby supernova would threaten all three at once. First comes the geomagnetic surge. When charged particles from the explosion slam into Earth's magnetic field, they twist it violently, creating electric currents that flow through the ground. Those surges can overload transformers and shut down power grids instantly. Nuclear reactors depend on those external grids to run their cooling systems. If the grid goes dark, the plants lose their lifeline. Next, the radiation pulse hits the satellites. Communication networks fail. GPS goes offline. Control signals between plants and national power operators vanish. In some cases, sensors might misread the radiation spike as a reactor malfunction, automatically triggering a scram, an emergency shutdown, where control rods drop into the core to halt the reaction. It's a safety mechanism designed to prevent meltdown. But when every reactor in the world does it at once during a global blackout, safety becomes chaos. After a scram, reactors still produce decay heat, about 6% of their normal output. That heat has to be removed by constant circulation of coolant. Normally, that's done with electric pumps. But if the power grid is gone and backup generators fail under geomagnetic stress, cooling stops. And without cooling, even a safe shutdown reactor can overheat within hours. We've seen small versions of this before. In 1989, a solar storm tripped circuits in Quebec and briefly threatened Canadian reactors. In 2011, after Japan's tsunami cut power to Fukushima, cooling systems failed, and within days, the cores melted down. Now scale that up to a global level. Hundreds of reactors suddenly without communication, backup power, or working sensors. Operators unsure whether they're seeing radiation from the reactor or from the supernova itself. Emergency protocols colliding. In the best case, everything shuts down safely, lights off, silence, and miles of concrete domes standing still under starlight. In the worst case, dozens of reactors melt down simultaneously, spreading contamination into air, rivers, and oceans, a radioactive echo of the cosmic explosion that caused it. And it all begins before anyone even knows what's happening. The gamma rays would hit in seconds, the geomagnetic surges minutes later. Long before astronomers could confirm the dying star's location, the world's power grid and its nuclear guardians would already be shutting themselves down. A dying star light years away could make humanity's own stars, the ones we built in concrete shells, flicker, fail, and fall silent. The universe wouldn't even notice. Airplanes in flight could lose all avionics mid-air. You're 35,000 feet above the ocean. It's midnight. The seatbelt sign glows softly. The engines hum, steady and calm. Somewhere below, a few lights glimmer on distant islands. And then, suddenly, every screen in the cockpit goes dark. No radar, no GPS, no radio, no way to tell up from down. That's what a nearby supernova could do to every airplane in the sky. When a star explodes, the first wave that reaches Earth isn't the shock wave or debris, it's radiation. A storm of gamma rays, X-rays, and charged particles moving at the speed of light. Those high-energy bursts can ionize Earth's upper atmosphere, turning it into an electrical nightmare. And that's exactly where planes fly. Commercial jets cruise in the lower stratosphere, around 10 kilometers up, the perfect altitude for efficient travel, but also the perfect target for radiation. Normally, the atmosphere above shields them from most cosmic rays, but if a nearby supernova floods the planet with radiation, that protection evaporates in seconds. Electronics in airplanes, called avionics, are built for reliability. They can survive lightning strikes and mild solar storms, but they're not built to endure a gamma-ray pulse that slams through their circuits like an invisible hammer. Every aircraft relies on dozens of interconnected systems, flight control computers, GPS receivers, radio transponders, pressure sensors, autopilot modules. Each one depends on delicate microchips that store and process information. A single energetic particle can flip bits in those chips. It's called a single-event upset. Usually it's rare. During a supernova's radiation surge, it would happen billions of times per second. The effect? Chaos in the sky. Autopilots would shut off, navigation systems would go blind, communication would vanish as satellites and ground relays died. Pilots trained to rely on digital instruments would suddenly face a blank cockpit, no altitude, no heading, no speed. In the dark, thousands of planes over oceans and continents would lose their bearings at once. Air traffic control would be useless, radio frequencies jammed by atmospheric ionization. Even analog backups, magnetic compasses, and gyroscopes might be unreliable, warped by electromagnetic interference from the same radiation storm. And it wouldn't stop with the electronics. High doses of radiation at flight altitude could harm passengers and crews directly, increasing exposure to hundreds of times normal levels in just minutes. Pilots might try to descend below the radiation-rich layers of atmosphere, but without guidance, that's guesswork. Landing blind in stormy skies, with jammed communication and failing instruments, would test the limits of human skill. In short, a dying star light years away could turn modern aviation into a mid-air ghost fleet. Hundreds of silent planes drifting through turbulent skies, their lights blinking out one by one. It wouldn't be war, it wouldn't be sabotage, it would be physics, the raw, unstoppable kind that doesn't care how advanced we think we are. The next morning, the sky would be empty. No contrails, no flights, no sound but the wind. A star's death would have reached across space,
and pulled us, quite literally, out of the sky.
Astronauts on the ISS would have no protection. From the ground, the International Space Station looks like a slow-moving star, a tiny light gliding across the night sky. People wave at it. Kids track it on phone apps. It feels distant but safe, a symbol of human achievement floating above our troubles. But if a nearby star exploded, that small light in orbit would become the most dangerous place in the solar system. A supernova doesn't just send light, it hurls out gamma rays and high-energy particles powerful enough to shred atoms. On Earth, our thick atmosphere absorbs most of that radiation before it ever reaches the ground. In orbit, the ISS has no such shield. Its protection is a few millimeters of aluminum and composite panels, enough to stop dust, but not death. When the radiation wave arrives, there would be no warning, no flash, no sound, just an invisible storm traveling at the speed of light. The first thing to die wouldn't be the astronauts, it would be the machines. Sensors would glitch, computers would short, power systems would flicker as gamma rays tore through microchips. Communication with Earth would fade to static. Then the wave would reach the crew. Inside their suits and modules, the radiation dose would spike to thousands of sieverts, more than enough to kill a human in seconds. Gamma rays pass through metal, through water, through flesh. They tear apart DNA, ionize molecules, and flood tissues with electrical chaos. There's no pain, no flame, just cellular destruction faster than thought. Even if the astronauts fled to the most shielded section of the station, water tanks, supply walls, or emergency capsules, it wouldn't save them. The exposure would be absolute. And the cruelest part? They'd see it first. Before anyone on Earth realized what happened, they'd be looking directly at the cosmic blast, a sudden light on the horizon, brighter than the moon, flooding their eyes with ghostly radiance. For a few seconds, it would be beautiful. For the next few moments, fatal. The station itself would survive, but empty. A silent shell orbiting a planet that wouldn't yet know what it had lost. Down below, scientists would still be waiting for the first visible signs of the supernova, unaware that the crew above had already absorbed its invisible fury. We tend to think of space as freedom, as the edge of human courage, but in truth it's a thin bubble of safety in an ocean of lethal energy. If a nearby star went supernova, that fragile bubble would burst instantly, and in the quiet that followed, Earth would still spin below, protected by its blanket of air, while the ghosts of its bravest explorers drifted overhead, lit by the glow of the very thing that killed them, a reminder that sometimes the first to see the wonders of the universe are also the first to die from them. Governments might mistake the flash for nuclear war. It starts with light, a sudden blinding flash that cuts across the sky, brighter than the moon, sharper than lightning, and visible from every hemisphere at once. For a few moments, the night turns to day. Inside military command bunkers, alarms erupt. Satellites detect an intense burst of gamma radiation spreading over the planet. Early warning systems classify it instantly. Possible nuclear detonation. But this one doesn't come from any known launch site. It comes from space. In a world where nuclear response systems are designed to act within minutes, even seconds, that's enough to set off global panic. Commanders scramble, hotlines go active, radar screens light up. The US, Russia, China, every nuclear-armed nation suddenly sees the same terrifying data. A blinding flash, an electromagnetic surge, communication disruptions, and satellites failing one after another, and no one knows why. To them, it looks like a mass EMP strike, the opening move of all-out war. Power grids flicker, GPS drops, military satellites go dark, and high-frequency radio becomes static. It's textbook, first strike chaos. The protocols that were meant to save humanity from destruction now hang by a thread, waiting for one panicked interpretation. Meanwhile, astronomers, the only people who might recognize what's happening, can't get a signal out. Observatories lose contact, telescopes go offline, data lines die with the satellites. The world's communication network collapses just when the truth matters most. It's the kind of moment that history was built to fear. The Cuban Missile Crisis, but silent. No diplomats, no phone calls, just blinking screens and missing information. In the first minutes after a nearby supernova's gamma ray burst, the confusion would be total. NORAD and other defense networks are designed to respond to nuclear flashes using space-based sensors. Those same sensors would detect the cosmic radiation as a worldwide detonation signature. The odds of misreading it as an attack would be terrifyingly high. And panic doesn't wait for confirmation. Submarine fleets go on alert. Strategic bombers scramble. Political leaders are rushed to underground bunkers. In some countries, automated dead-hand retaliation systems designed to launch nuclear weapons if command is lost could start ticking toward activation. All because a star died. By the time scientists managed to confirm that the radiation came from deep space, not Earth's surface, the world might already be seconds from irreversible decisions. The irony is cruel. The universe gives us a light show, and we answer it with missiles. Eventually, the data would settle. The panic would fade. The governments would stand down, but the realization would linger. We almost destroyed ourselves because of a mistake written in starlight. Every sensor, every radar, every satellite humanity built to protect itself would have been fooled by the oldest illusion in the cosmos, a flash from something that died long before we even existed. A single dying star, hundreds of light years away, nearly convincing an entire species that it had just destroyed itself. That's not science fiction. That's how fragile civilization really is. One bright flash away from ending by its own hand. Panic-driven mass migrations from exposed regions would occur. Fear moves faster than light. Before the shock wave ever touches us, before the scientists finish their press conferences, the world's population would already be on the move. When news breaks that a nearby star has exploded, no one will wait for detailed analysis. Headlines would scream words like radiation, fallout, and danger zone. Maps would circulate online showing speculative safe regions, half based on data, half on rumor. Within hours, highways would clog, airports would overflow. It wouldn't matter that the atmosphere blocks most radiation, or that experts plead for calm. Once the public hears the phrase supernova near Earth, rationality goes extinct. People living near the equator might assume they're closer to the blast.
even if that's not true. Northern and southern latitudes might believe they're in the line of fire. Entire regions would brand themselves unsafe simply because of proximity or superstition. Anyone with money or mobility would start moving toward what they think is safety: mountain ranges, underground shelters, or distant rural towns. And, as always, misinformation would lead to charge. Social media would amplify every rumor: radiation cloud incoming, government hiding true impact, only underground areas are safe. Videos of auroras caused by magnetic disturbances would be mistaken for atmospheric burning. People would post live feeds of the sky, counting down to what they believe is the end. This kind of panic migration has happened before, even without cosmic threats. During nuclear scares, pandemics, and volcanic warnings, millions have fled perceived danger zones, often into worse conditions. But this time, it wouldn't be local, it would be global. Cities would empty overnight. Coastal highways would lock in gridlock, stretching for hundreds of kilometers. Fuel would vanish first, then food, then order. Governments would attempt to impose martial law, but even soldiers panic when they think the sky itself is falling. Richer nations would see waves of refugees from poorer ones, families desperate to cross borders to radiation-safe zones. Camps would appear in deserts, mountains, and forests. For the first time, humanity would experience a cosmic refugee crisis, not driven by war, but by the terror of the unknown. Ironically, those fleeing might already be safe. The true danger from a nearby supernova, gamma rays, and ozone loss takes years to fully show its effects. But fear doesn't care about science. Fear moves people. Anthropologists call this phenomenon collective flight behavior, a survival instinct gone wild when information becomes uncertain. In the supernova scenario, that instinct would ignite on a planetary scale. Decades later, historians would call it the Great Migration of Light. Entire generations displaced not by famine, not by politics, but by a flash in the sky that convinced billions the world was ending. And maybe, in a way, it did. Not the physical world, but the psychological one. Because once humanity sees the heavens themselves as a threat, every sunrise starts to feel like a countdown. The star dies once, but the panic it triggers, that could reshape civilization forever.
Stock markets would crash as satellite systems go offline. Money doesn't need fire or war to vanish. It just needs silence, the kind that comes when satellites stop talking. In the modern world, every stock trade, bank transfer, and cryptocurrency transaction depends on one fragile thing: timing, down to the microsecond. When you buy a share of stock, it isn't a simple button click. It's a dance between satellites, servers, and global networks syncing time signals from orbit. Those signals come from GPS satellites, which don't just tell us where we are, they tell us when we are. Every trade in the global market is time-stamped by those signals. Without them, the system can't function. Now picture this. A nearby supernova erupts. Within seconds, gamma rays and high-energy particles slam into the Earth's magnetic field, frying satellites like bugs under a magnifying glass. Communication relays die. GPS goes silent. Radio signals distort in the ionized atmosphere. The stock market doesn't wait for clarification, it collapses instantly. Trading algorithms, which make up the majority of modern trades, depend entirely on precise time synchronization. Once that synchronization fails, trades are processed out of order or lost completely. Within minutes, data centers start receiving corrupted feeds. Prices flicker uncontrollably. Panic sells flood the system. At first, traders think it's a cyber attack. Then they realize no one's system is working. The screens still glow, but the information on them is worthless. The New York Stock Exchange halts trading. London follows. Tokyo freezes. Within an hour, global financial markets grind to a halt, not because of a crash in value, but because of information failure. Banks can't clear payments. ATMs stop responding. The systems that handle everything from mortgages to payroll to energy trading go dark. Entire economies go into cardiac arrest, and there's no technician to reboot the universe. And then comes the panic. People rush to withdraw cash. Digital currencies crash. No internet, no blockchain validation. Supply chains that rely on automated contracts stop mid-transaction. Governments issue emergency statements, but without functioning satellites, even their broadcasts are intermittent. The irony is brutal. The supernova hasn't even physically touched Earth yet. The atmosphere is intact. Cities are still lit, but civilization's nervous system, its digital bloodstream, has already failed. Economists would later call it the silent crash, not caused by greed, speculation, or policy, but by physics. A reminder that our trillion-dollar markets sit on foundations thinner than we think. The most powerful economies in human history would fall apart because a star thousands of light years away decided to die. And when the dust settled, it wouldn't just be money we lost. It would be trust, the belief that our systems are unbreakable, the illusion that technology makes us invincible, all gone in the blink of a cosmic flash. The markets would recover someday, of course. They always do. But this time, every trader, every investor, every government would remember one thing. It wasn't inflation. It wasn't a policy. It was a dead star. And it reminded the richest planet in the universe just how fragile its wealth really is. Religions might interpret the event as an omen or judgment day. Humanity has always looked to the sky for meaning. It's where we placed our gods, our hopes, our fears. So when the heavens suddenly blaze brighter than anything in recorded history, a light so fierce it erases the stars, it wouldn't just be seen as an event, it would be seen as a sign. When a nearby star explodes, the flash would outshine the moon and be visible even during daylight. For weeks or months, people around the world would wake to a sky that feels wrong, familiar but changed. No matter how rational the explanations, the emotional reaction would be ancient. The same instincts that once saw eclipses as omens or comets as curses would awaken instantly. In temples, churches, and mosques, the sermons would begin before the science. Some would call it a harbinger, a message that the end is near, that humanity has angered something higher. Apocalyptic verses would flood the airwaves, drawing from every scripture imaginable, the book of Revelation, the Quranic signs of Qiyamah, the Hindu Kali Yuga, the Mayan cycles of destruction and rebirth. Each would seem to fit the light
perfectly, as if the cosmos itself had turned its gaze upon us. Religious leaders would divide in interpretation. Some would see hope, the birth of a new age, a celestial cleansing. Others would see punishment, a reckoning for humanity's arrogance. Millions would seek comfort in prayer, pilgrimages, or mass gatherings, but just as many would be gripped by fear. In some regions, spontaneous rituals might erupt, people lighting candles under the glowing sky, confessing sins in public, donating their possessions, preparing for deliverance. Social media would magnify it all. Videos of the mysterious new star, hashtags about divine judgment, global audiences feeding off collective awe and terror. Governments would try to control the narrative, but you can't out-communicate prophecy. Once something in the heavens changes, belief spreads faster than facts. History already gives us clues. When Halley's Comet appeared in 1066, it was called the Sword of Heaven. When a supernova lit the sky in 1054, Chinese astronomers recorded it calmly, but across the world, other cultures feared it as divine warning. Now, imagine that multiplied by 8 billion people, all staring up at the same unblinking light. Even decades later, theologians would still debate it. Was it a coincidence, or was it cosmic scripture, the universe reminding us of our place beneath it? Perhaps the truth lies somewhere in between. A supernova is the death of a star, yes, but it also creates new elements, new worlds, and new beginnings. Maybe it's not punishment or promise, but a cycle written into existence itself. Destruction, feeding creation. For some, it would be science. For others, faith. But for everyone, it would feel deeply personal. A moment when the universe seemed to whisper directly to the human soul. And long after the light fades, one question would remain. Was it just a dying star, or was it something trying to get our attention?
Surviving underground societies might become permanent. At first, they'd go below just to wait it out. A few months underground until the radiation passed, maybe a few years until the atmosphere healed. But when they finally tried to go back up, they might decide not to. When a nearby star explodes, surface life takes the brunt of it. Gamma radiation, ultraviolet floods, and cosmic rays slicing through the atmosphere like invisible knives. The upper ozone thins, sunlight becomes poison, crops die, and oceans bloom with toxic algae. Survival on the surface becomes less about endurance and more about avoidance. Governments, corporations, and wealthy private groups would race to build underground shelters, the same bunkers originally designed for nuclear war. Subterranean cities with filtered air, recycled water, and artificial sunlight. What starts as emergency refuge quickly evolves into a new kind of civilization. Humans are adaptable. Once we dig in, we start decorating the walls. At first, these underground societies would plan for return. Calendars counting down to surface day, schedules for re-emergence. But as months turn to years and the world above remains unstable, priorities shift. Children are born who've never seen the sky. They don't miss it. The tunnels become home. Soon, practical concerns become cultural ones. Why risk radiation, famine, and ultraviolet exposure when life below is predictable? Underground communities develop their own economies, their own power structures. Artificial daylight follows strict schedules to mimic circadian rhythms. Entertainment shifts from stargazing to simulation. Holographic horizons replacing real ones. On the surface, only ruins and wild ecosystems remain. Radiation-resistant plants, insects, and scavengers dominate. The earth begins to heal in strange, alien ways. Forests of mutations and silence. But below, humanity thrives in echoing corridors of steel and recycled air. Sociologists have speculated about this before, how isolation reshapes societies. Without direct sunlight, vitamin D deficiencies lead to genetic adaptation. Without weather, architecture evolves inward. Without stars, spirituality changes too. The old religions that looked up might fade, replaced by new philosophies that look within, the ceiling becoming the new sky. Generations later, if someone ventured up to the surface, they might find it unrecognizable, a planet slowly reclaiming itself, and a humanity that forgot what open air felt like. Communication between surface and subsurface worlds might vanish entirely, each adapting to its own environment. The surface dwellers would become mythic figures, ghosts of a sunlit age. In the long view of evolution, this isn't far-fetched. Species have gone underground before, during mass extinctions, volcanic winters, or ice ages. Humanity would simply be continuing the trend, but voluntarily. And when those underground cities grow and spread, when their descendants look back through ancient archives and see what forced their ancestors below, the story will sound almost poetic. A dying star lit the heavens, and humanity, afraid of the light, built a new world in the dark. Not as refugees, but as the next version of civilization. Human cultures could split into surface and underground tribes. Every great disaster doesn't just destroy, it divides. After the supernova, humanity wouldn't simply vanish, it would fracture. Once the surface becomes hostile, seared by radiation, stripped of ozone, battered by ultraviolet storms, billions would seek safety below ground. But not everyone could make it. Some would stay above out of necessity, defiance, or faith. And over the years, that simple difference, who went below and who stayed above, would evolve into something far deeper. At first, the split would be practical. The subterraneans would live in sealed megastructures and underground cities powered by geothermal energy. Artificial lights would mimic day and night. Crops would grow under LEDs, and their culture would revolve around stability, control, and caution. The surface dwellers, by contrast, would adapt to exposure, scavenging among ruins, sheltering in caves, and evolving under a harsher, mutating world. But generations later, the split would stop being about geography. It would become identity. The subterraneans might come to see the surface world as primitive and dangerous, a mythic wasteland filled with chaos and disease. Their children would grow up under artificial skies, pale-skinned, wary of radiation, taught that their ancestors escaped the curse of the sun. Meanwhile, the surface dwellers would evolve their own worldview, reverent toward the sky that nearly killed them,
treating the lingering glow of the supernova as sacred. They'd see themselves as the true inheritors of Earth, the ones who endured the wrath of heaven and lived. To them, the underground people wouldn't be survivors, they'd be cowards hiding from destiny. Trade might exist at first, minerals, crops, medicine, but mistrust would grow. Myths would follow. Subterraneans would tell stories of sunburned raiders who crawl out of the wasteland at night. Surface dwellers would whisper about pale ghosts who never see the light, feeding off the earth's warmth. Language would diverge, customs too. One culture shaped by confinement, technology, and routine, the other by endurance, faith, and instinct. Even physiology might drift apart. Different diets, radiation exposure, and generations of isolation changing body types, skin tone, and tolerance to the environment. And so, from one species, two societies would bloom, not by choice, but by adaptation. History shows it always happens this way. When climate changes, when continents split, when survival requires new environments, cultures diverge. After a nearby supernova, the split would be planetary. Centuries later, they might meet again. An expedition from the deep tunnels climbing to the surface. A caravan of nomads descending into the earth for trade or curiosity. Each side staring at the other, realizing they share ancestry, but not memory. To the subterraneans, sunlight would seem unbearable. To the surface dwellers, the underground air would feel suffocating. They'd speak different languages, wear different symbols, and worship different gods, one rooted in darkness, the other in light. All because a star died, and in doing so, it forced humanity to divide along the oldest fault line of all, above and below.
Myths about a second sun would dominate future religions. Centuries after the explosion, when the science is forgotten, but the stories remain, people will still look to the sky and talk about the day of two suns. Long after the instruments have rusted and the data is gone, the memory of that brightness, that ghostly, impossible light that burned in the heavens for months, will survive the only way humans know how to preserve something cosmic, through myth. The supernova's glow would have been unforgettable. For weeks or even years, Earth would have two lights, our familiar sun and another, colder one, burning high among the stars. It wouldn't move across the sky, but it would shine night and day, casting strange twin shadows. Farmers would work by it, poets would write under it, children would be born into a world that felt blessed or cursed by the heavens. When it finally faded, the hole it left in the sky would ache like a memory, and from that ache stories would grow. Some cultures would call it the second sun, a divine flame that appeared when humanity lost its way. Others would call it the eye of God, watching silently from the void. In more fatalistic traditions, it might be seen as the scar of judgment, a reminder that the universe once looked directly at us and found us wanting. The mythologies would differ, but their roots would be shared: awe, fear, and the need to make meaning from light. In oral traditions, the event might merge with prophecy. When two suns rise, the old world ends. Future generations might weave it into creation stories, the first sun for life, the second for rebirth. Temples could align their architecture to where the supernova once burned, just as ancient civilizations aligned monuments to solstices and stars. Archaeologists in that future would find carvings of twin circles, sacred murals of double dawns, and hymns describing the year the sky caught fire. They'd argue endlessly over whether it was allegory or truth, not realizing that once it really happened. And for those who keep records, the tale would deepen into theology. The second sun could become the centerpiece of entire religions, representing enlightenment, punishment, or cosmic renewal. Philosophers might write that the two suns symbolize the dual nature of existence, creation and destruction, knowledge and ignorance, light and shadow. In time, even the supernova's scientific explanation, once clear to astronomers, would dissolve into legend. Facts fade faster than faith. Thousands of years later, when someone looks up at the night sky and notices a faint nebula, the still glowing remnant of that ancient star, they might whisper prayers to it, never realizing they're speaking to the ashes of what once nearly killed their ancestors. It's always been this way. Eclipses became omens, comets became prophecies, and when a dying star lit the earth with its last breath, humanity did what it always does. It turned catastrophe into scripture. The universe may write in radiation, but humans translate it into meaning. And so, even after the light fades, the story of the second sun would burn forever, not in the sky, but in belief. A radiation-shielded economy would form. Civilizations don't stop, they reshape. When the surface becomes dangerous and sunlight turns toxic, humanity won't surrender. It'll build a new kind of economy, one designed not for growth, but for survival. After a nearby supernova, radiation floods Earth's upper atmosphere. The ozone thins, ultraviolet levels skyrocket, and the surface becomes lethal during daylight. Within months, agriculture collapses, trade halts, and energy networks fail. But humanity's true superpower has never been strength, it's adaptation. The world that rises from that chaos would look alien, but strangely functional. The first survivors would focus on shielded food production. Traditional farms would die quickly under UV exposure, so food would move underground. Hydroponic systems inside domes, tunnels, and salt mines would replace open fields. Crops like algae, mushrooms, and lab-grown meat would dominate the diet. Artificial LEDs, powered by geothermal or nuclear sources, would replace sunlight entirely. A loaf of bread might cost what gold once did. Above ground, massive radiation domes would cover the ruins of old cities. Translucent shells made of layered glass, carbon fiber, and water-filled shielding panels. Inside, life would continue cautiously. Markets, hospitals, research labs, and trade hubs built under artificial skies. Outside, unprotected land would be mined by robots and radiation-resistant machines. And so a new economy of shelter would emerge. Mining operations would flourish underground, digging deeper than ever before, not for luxury, but for necessity.
Uranium, lithium, rare earth elements, all essential for powering domed cities and shielded farms. Entire industries would form around producing lead composites, magnetic shielding, and radiation-proof textiles. Currency would shift too. Gold might lose its appeal when survival materials, water filters, power cells, and air recyclers become the new wealth. Economies would pivot from digital trading to barter and physical exchange, especially when satellite-based banking collapses. Safe labor zones would replace free markets. Work becomes literal survival, tending underground crops, maintaining air systems, mining fuel. And as with every great shift, inequality would find a way to survive too. The wealthy would live in deep protected colonies with simulated daylight, gardens, and art. The poor would work in exposure zones, repairing domes and handling contaminated equipment for food credits. Over time, the surface worker would become a caste of its own, hardened, short-lived, and vital. Even culture would follow the economy underground. Festivals might be timed to artificial dawn cycles. Children would grow up never seeing the real sky. Art would be built from salvaged metals and recycled plastic, beauty shaped from the remnants of a burned world. In a few generations, this wouldn't feel temporary. It would feel normal. Economists of the future might call it the shielded age, a civilization reborn beneath its own skin. It's ironic, really. A dying star light years away could end capitalism, destroy global trade, and still inspire humanity to invent a brand new system, one where sunlight is currency and safety is the only wealth that matters. We'd adapt, as we always do, not because we want to thrive, but because extinction is bad for business.
Humanity might adapt biologically to higher radiation levels. Extinction isn't our only trick. Sometimes, when the universe turns hostile, life doesn't die, it changes. After a nearby star explodes, the Earth would be bathed in radiation far beyond anything life has faced in recorded history. The ozone layer would erode, ultraviolet light would pour through, and cosmic rays would rain down for generations. Most species would vanish, but humanity has never been most species. At first, survival would depend on technology, domes, shielding, underground cities. But over centuries, biology would begin to take over where machines leave off. Radiation would no longer be just an environmental hazard. It would become an evolutionary pressure. DNA, constantly bombarded by energetic particles, would mutate at unprecedented rates. Most of those mutations would be lethal: miscarriages, deformities, genetic illnesses. But a few, by pure chance, would help. And evolution loves an accident that works. Children born with slightly more efficient DNA repair enzymes would live longer. Those whose cells could tolerate oxidative damage better would reproduce more. Skin might darken and thicken not from sunlight, but from a need to block deeper spectrum ultraviolet rays. Over hundreds of generations, humanity's descendants could become something subtly different, not superhuman, just adapted. Some scientists have already glimpsed the possibility. There are microbes thriving in nuclear reactors, fungi growing on Chernobyl's ruins that literally feed on radiation,
converting gamma rays into energy through a pigment called melanin. If simple organisms can evolve that trick in a few decades, imagine what a determined species with intelligence and desperation could achieve in a few thousand years. Genetic engineering would accelerate the process. Once society stabilizes underground, researchers would begin editing genes to mimic radiation-hardened organisms, borrowing repair enzymes from tardigrades, melanin mechanisms from fungi, or even constructing artificial chromosomes designed for radiation tolerance. The line between natural evolution and self-directed adaptation would blur completely. And slowly, the descendants of those who lived through the Great Star Event might step back to the surface again, not in suits or domes, but as something new. They might see ultraviolet light as a visible color. Their immune systems could rebuild cells faster than radiation can destroy them. Hairless, melanin-rich skin might shimmer faintly under cosmic light. Humanity would have become, in every sense, a child of the stars, shaped by the same forces that once tried to erase it. Culturally, they'd remember the supernova not as a tragedy, but as a beginning. The moment Earth's fragile species stopped hiding from the cosmos and started adapting to it. Myths would call them the Resilients, the Daughters of Light, or the Second Race. Evolution doesn't care about comfort or legacy. It only asks one question: can you survive what comes next? And in the ruins of a planet once scorched by starlight, the answer might echo softly through the centuries. Yes, we didn't just survive the radiation, we became it.